the neural networks and how they have developed over time. So roughly 4 years ago, the car was mostly driving in a single lane, going forward on the highway. And so it had to keep lane, and it had to keep distance away from the car in front of us. And at that time, all of processing was only on individual image level. So a single image has to be analyzed by a neural net and make little pieces of the vector space, process that into little pieces of the vector space. So this processing took the following shape. We take 1280 by 960 input, and this is 12-bit integers streaming in at roughly 36 hertz. Now we're going to process that with a neural network. So we instantiate a feature extractor backbone. In this case, we use residual neural networks. So we have a stem and a number of residual blocks connected in series. Now, the specific class of ResNets that we use are RegNets, because RegNets offer a very nice design space for neural networks because they allow you to very nicely trade off latency and accuracy. Now, these RegNets give us, as an output, a number of features at different resolutions and different scales. So in particular, on the very bottom of this feature hierarchy, we have very high resolution information with very low channel counts. And all the way at the top, we have low resolution spatially, but high channel counts. So on the bottom, we have a lot of neurons that are really scrutinizing the detail of the image. And on the top, we have neurons that can see most of the image and a lot of that context, have a lot of that scene context. We then like to process this with feature pyramid networks. In our case, we like to use BiFPNs. And they get to multiple scales to talk to each other effectively and share a lot of information. So for example, if you're a neuron all the way down in the network and you're looking at a small patch and you're not sure if this is a car or not, it definitely helps to know from the top layers that, hey, you are actually in the vanishing point of this highway. And so that helps you disambiguate that this is probably a car. After a BiFPN and a feature fusion across scales, we then go into task-specific heads. So for example, if you are doing object detection, we have a one-stage YOLO-like object detector here where we initialize a raster, and there's a binary bit per position telling you whether or not there's a car there. And then in addition to that, if there is, here's a bunch of other attributes you might be interested in. So the XY with height offset, or any of the other attributes, like what type of a car is this, and so on. So this is for the detection by itself. Now, very quickly we discovered that we don't just want to detect cars, we want to do a large number of tasks. So, for example, we want to do traffic light recognition and detection, a lane prediction, and so on. So very quickly, we converged this kind of an architectural layout where there's a common shared backbone and then branches off into a number of heads. So we call these, therefore, HydraNets, and these are the heads of the Hydra. Now, this architectural layout has a number of benefits. So number one, because of the feature sharing, we can amortize the forward pass inference in the car at test time. And so this is very efficient to run. Because if we had to have a backbone for every single task, that would be a lot of backbones in the car. Number two, this decouples all of the tasks, so we can individually work on every one task in isolation. And for example, we can uprev any of the data sets or change some of the architecture of the head and so on. And you are not impacting any of the other tasks. And so we don't have to revalidate all the other tasks, which can be expensive. And number three, because there's this bottleneck here in features, what we do fairly often is that we actually cache these features to disk. And when we are doing these fine-tuning workflows, we only fine-tune from the cached features up and only fine-tune the heads. So most often, in terms of our training workflows, we will do an end-to-end training run once in a while, where we train everything jointly. Then we cache the features at the multi-scale feature level. And then we fine-tune off of that for a while. And then end-to-end train once again, and so on. So here's the kinds of predictions that we were obtaining, I would say, several years ago now, from one of these HydraNets. So again, we are processing individual images. There we go. We are processing just individual image, and we're making a large number of predictions about these images. So for example, here you can see predictions of the stop signs, the stop lines, the lines, the edges, the cars, the traffic lights, the curbs here, whether or not the car is parked. All of the static objects like trash cans, cones, and so on, and everything here is coming out of the net, here in this case, out of the HydraNet. So that was all fine and great, but as we worked towards FSD, we quickly found that this is not enough. So where this first started to break was when we started to work on Smart Summon. Here I am showing some of the predictions of only the curb detection task, and I'm showing it now for every one of the cameras. So we'd like to wind our way around the parking lot to find the person who is summoning the car. Now, the problem is that you can't just directly drive on image space predictions. You actually need to cast them out and form some kind of a vector space around you. So we attempted to do this using C++ and developed what we called the occupancy tracker at the time. So here we see that the curb detections from the images are being stitched up across camera scenes, camera boundaries, and over time. Now, there were two major problems, I would say, with this setup. Number one, we very quickly discovered that tuning the occupancy tracker and all of its hyperparameters was extremely complicated. You don't want to do this explicitly by hand in C++. You want this to be inside a neural network and train that end to end. Number two, we very quickly discovered that the image space is not the correct output space. You don't want to make predictions in image space. You really want to make it directly in the vector space. So here's a way of illustrating the issue. So here I'm showing on the first row the predictions of our curbs and our lines in red and blue. And they look great in the image, but once you cast them out into the vector space, things start to look really terrible, and we are not going to be able to drive on this. So you see how the predictions are quite bad in vector space, and the reason for this fundamentally is because you need to have an extremely accurate depth per pixel in order to actually do this projection. And so you can imagine just how high of a bar it is to predict that depth so accurately in every single pixel of the image. And also, if there's any occluded area where you'd like to make predictions, you will not be able to because it's not an image space concept in that case. So we very quickly the other problems with this, by the way, is also for object detection. If you are only making predictions per camera, then sometimes you will encounter cases like this where a single car actually spans 5 of the 8 cameras. And so if you are making individual predictions, then no single camera sees all of the car. And so obviously you're not going to be able to do a very good job of predicting that whole car. And it's going to be incredibly difficult to fuse these measurements. So we have this intuition that what we'd like to do instead is we'd like to take all of the images and simultaneously feed them into a single neural net and directly output in vector space. Now, this is very easily said, much more difficult to actually achieve. But roughly, we want to lay out a neural net in this way, where we process every single image with a backbone, and then we want to somehow fuse them, and we want to re-represent the features from image space features to directly some kind of a vector space features, and then go into the decoding of the head. Now, so there are two problems with this. Problem number one, how do you actually create the neural network components that do this transformation? And you have to make it differentiable so that end-to-end training is possible. And number two, if you want vector space predictions from your neural net, you need vector space data sets. So just labeling images and so on is not going to get you there. You need vector space labels. We're going to talk a lot more about problem number two later in the talk. For now, I want to focus on the neural network architectures, so I'm going to deep dive into problem number one. So here's the rough problem, right? We're trying to have this bird's eye view prediction instead of image space predictions. So for example, let's focus on a single pixel in the output space in yellow. And this pixel is trying to decide, am I part of a curb or not, as an example. And now, where should the support for this kind of a prediction come from in the image space? Well, we know roughly how the cameras are positioned and their extrinsics and intrinsics, so we can roughly project this point into the camera images. And the evidence for whether or not this is a curb may come from somewhere here in the images. The problem is that this projection is really hard to actually get correct because it is a function of the road surface. The road surface could be sloping up or sloping down, or also there could be other data-dependent issues. For example, there could be an occlusion due to a car. So if there's a car occluding this viewport, this part of the image, then actually you may want to pay attention to a different part of the image, not the part where it projects. And so because this is data-dependent, it's really hard to have a fixed transformation for this component. So in order to solve this issue, we use a transformer to represent this space. And this transformer it uses multi-headed self-attention and blocks of it. In this case, actually, we can get away with even a single block doing a lot of this work. And effectively what this does is you initialize a raster of the size of the output space that you would like, and you tile it with positional encodings with sines and coses in the output space. And then these get encoded with an MLP into a set of query vectors. And then all of the images and their features also emit their own keys and values. And then the query's keys and values feed into the multi-headed self-attention. And so effectively what's happening is that every single image piece is broadcasting in its key what is it a part of. So hey, I'm part of a pillar in roughly this location, and I'm seeing this kind of stuff. And that's in the key. And then every query is something along the lines of, hey, I'm a pixel in the output space at this position, and I'm looking for features of this type. Then the keys and the queries interact multiplicatively, and then the values get pooled accordingly. And so this re-represents the space, and we found this to be very effective for this transformation. So if you do all of the engineering correctly, this again is very easily said, difficult to do. You do all of the engineering correctly, there's one more problem actually before. I'm not sure what's up with the slides. So one more thing, you have to be careful with some of the details here when you are trying to get this to work. So in particular, all of our cars are slightly cockeyed in a slightly different way. And so if you're doing this transformation from image space to the output space, you really need to know what your camera calibration is. And you need to feed that in somehow into the neural net. And so you could definitely just like concatenate the camera calibrations of all of the images and somehow feed them in with an MLP. But actually, we found that we can do much better by transforming all of the images into a synthetic virtual camera using a special rectification transform. So this is what that would look like. We insert a new layer right above the image, rectification layer. It's a function of camera calibration, and it translates all of the images into a virtual common camera. So if you were to average up a lot of repeater images, for example, which face to the back, without doing this, you would get a kind of a blur. But after doing the rectification transformation, you see that the back mirror gets really crisp. So once you do this, this improves the performance quite a bit. So here are some of the results. So on the left, we are seeing what we had before, and on the right, we're now seeing significantly improved predictions coming directly out of the neural net. This is a multi-camera network predicting directly in vector space, and you can see that it's basically night and day. You can actually drive on this. And this took some time and some engineering and incredible work from the AI team to actually get this to work and deploy and make it efficient in the car. This also improved a lot of our object detection. So for example, here in this video, I'm showing single camera predictions in orange and multi-camera predictions in blue. And basically, if you can't predict these cars if you are only seeing a tiny sliver of a car. So your detections are not going to be very good, and their positions are not going to be good. But a multi-camera network does not have an issue. Here's another video from a more nominal sort of situation. And we see that as these cars in this tight space cross camera boundaries, there's a lot of jank that enters into the predictions. And basically, the whole setup just doesn't make sense, especially for very large vehicles like this one. And we can see that the multi-camera networks struggle significantly less with these kinds of predictions. OK, so at this point, we have multi-camera networks, and they're giving predictions directly in vector space. But we are still operating at every single instant in time completely independently. So very quickly, we discovered that there's a large number of predictions we want to make that actually require the video context, and we need to somehow figure out how to feed this into the net. So in particular, is this car parked or not? Is it moving? How fast is it moving? Is it still there, even though it's temporarily occluded? Or for example, if I'm trying to predict the road geometry ahead, it's very helpful to know if the signs or the road markings that I saw 50 meters ago. So we try to develop, we try to insert video modules into our neural network architecture, and this is kind of one of the solutions that we've converged on. So we have the multi-scale features, as we had them from before, and what we are going to now insert is a feature queue module that is going to cache some of these features over time, and then a video module that is going to fuse this information temporally. And then we're going to continue into the heads that do the decoding. Now, I'm going to go into both of these blocks one by one. Also, in addition, notice here that we are also feeding in the kinematics. This is basically the velocity and the acceleration that's telling us about how the car is moving. So not only are we going to keep track of what we're seeing from all the cameras, but also how the car has traveled. So here's the feature queue and the rough layout of it. We are basically concatenating these features over time and the kinematics of how the car has moved and the positional encodings, and that's being concatenated, encoded, and stored in a feature queue. And that's going to be consumed by a video module. Now, there's a few details here, again, to get right. So in particular, with respect to the pop and push mechanisms, and when do you push, and how, and especially when do you push, basically. So here's a cartoon diagram illustrating some of the challenges here. There's going to be the ego car is coming from the bottom and coming up to this intersection here, and then traffic is going to start crossing in front of us, and it's going to temporarily start occluding some of the cars ahead. And then we're going to be stuck at this intersection for a while and just waiting our turn. This is something that happens all the time and is a cartoon representation of some of the challenges here. So number one, with respect to the feature queue and when we want to push into a queue, obviously we'd like to have some kind of a time-based queue where, for example, we enter the features into the queue, say, every 27 milliseconds. And so if a car gets temporarily occluded, then the neural network now has the power to look and reference the memory in time and learn the association that, hey, even though this thing looks occluded right now, there's a record of it in my previous features, and I can use this to still make a detection. So that's kind of like the more obvious one, but the one that we also discovered is necessary in our case is, for example, suppose you're trying to make predictions about the road surface and the road geometry ahead, and you're trying to predict that I'm in a turning lane and the lane next to us is going straight. Then it's really necessary to know about the line markings and the signs, and sometimes they occur a long time ago. And so if you only have a time-based queue, you may forget the features while you're waiting at your red light. So in addition to a time-based queue, we also have a space-based queue. So we push every time the car travels a certain fixed distance. So some of these details actually can matter quite a bit. And so in this case, we have a time-based queue and a space-based queue to cache our features, and that continues into the video module. Now, for the video module, we looked at a number of possibilities of how to fuse this information temporally. So we looked at three-dimensional convolutions, transformers, axial transformers in an effort to try to make them more efficient, recurrent neural networks of a large number of flavors. But the one that we actually like quite a bit as well, and I want to spend some time on, is a spatial recurrent neural network video module. And so what we're doing here is, because of the structure of the problem, we're driving on two-dimensional surfaces, we can actually organize the hidden state into a two-dimensional lattice. And then as the car is driving around, we update only the parts that are near the car and where the car has visibility. So as the car is driving around, we are using the kinematics to integrate the position of the car in the hidden features grid. And we are only updating the RNN at the points where we have that are nearby us, sort of. So here's an example of what that looks like. Here, what I'm going to show you is the car driving around, and we're looking at the hidden state of this RNN. And these are different channels in the hidden state. So you can see that this is after optimization and training this neural net. You can see that some of the channels are keeping track of different aspects of the road. Like, for example, the centers of the road, the edges, the lines, the road surface, and so on. Here's another cool video of this. So this is looking at the mean of the first 10 channels in the hidden state for different traversals of different intersections. And all I want you to see basically is that there's cool activity as the recurrent neural network is keeping track of what's happening at any point in time. And you can imagine that we've now given the power to the neural network to actually selectively read and write to this memory. So for example, if there's a car right next to us and is occluding some parts of the road, then now the network has the ability to not write to those locations. But when the car goes away and we have a really good view, then the recurrent neural net can say, okay, we have very clear visibility. We definitely want to write information about what's in that part of space. Here's a few predictions that show what this looks like. So here we are making predictions about the road boundaries in red, intersection areas in blue, road centers, and so on. So we're only showing a few of the predictions here just to keep the visualization clean. And yeah, this is done by the spatial RNN. And this is only showing a single clip, a single traversal, but you can imagine there could be multiple trips through here, and basically a number of cars, a number of clips could be collaborating to build this map, basically and effectively an HD map, except it's not in the space of explicit items, it's in a space of features of a recurrent neural network, which is kind of cool. I haven't seen that before. The video networks also improved our object detection quite a bit. So in this example, I want to show you a case where there are two cars over there, and one car is going to drive by and occlude them briefly. So look at what's happening with the single frame and the video predictions as the cars pass in front of us. Yeah, so that makes a lot of sense. So a quick playthrough through what's happening. When both of them are in view, the predictions are roughly equivalent, and you are seeing multiple orange boxes because they're coming from different cameras. When they are occluded, the single frame networks drop the detection, but the video module remembers it, and we can persist the cars. And then when they are only partially occluded, the single frame network is forced to make its best guess about what it's seeing, and it's forced to make a prediction, and it makes a really terrible prediction. But the video module knows that there's only a partial, it has the information, and knows that this is not a very easily visible part right now, and doesn't actually take that into account. We also saw significant improvements in our ability to estimate depth, and of course, especially velocity. So here I'm showing a clip from our remove the radar push, where we are seeing the radar depth and velocity in green, and we were trying to match or even surpass, of course, the signal just from video networks alone. And what you're seeing here is in orange, we are seeing a single frame performance, and in blue, we are seeing, again, video modules. And so you see that the quality of depth is much higher. And for velocity, the orange signal, of course, you can't get velocity out of a single frame network, so we just differentiate depth to get that. But the video module actually is basically right on top of the radar signal. And so we found that this worked extremely well for us. So here's putting everything together. This is what our architecture roughly looks like today. So we have raw images feeding on the bottom, They go through a rectification layer to correct for camera calibration and put everything into a common virtual camera. We pass them through regnets, residual networks, to process them into a number of features at different scales. We fuse the multi-scale information with BiFBN. This goes through a transformer module to re-represent it into the vector space in the output space. This feeds into a feature queue in time or space that gets processed by a video module, like the spatial RNN, and then continues into the branching structure of the HydraNet with trunks and heads for all the different tasks. And so that's the architecture roughly what it looks like today. And on the right, you are seeing some of its predictions, sort of visualized both in a top-down vector space and also in images. So definitely, this architecture has definitely complexified from just a very simple image-based single network about 3 or 4 years ago and continues to evolve. It's definitely quite impressive now. There's still opportunities for improvements that the team is actively working on. For example, you'll notice that our fusion of time and space is fairly late in neural network terms. So maybe we can actually do earlier fusion of space or time and do, for example, cost volumes or optical flow-like networks on the bottom. Or for example, our outputs are dense rasters, and it's actually pretty expensive to post-process some of these dense rasters in the car. And of course, we are under very strict latency requirements, so this is not ideal. We actually are looking into all kinds of ways of predicting just the sparse structure of the road, maybe like point by point, or in some other fashion that doesn't require expensive post-processing. But this basically is how you achieve a very nice vector space. And now I believe Ashok is going to talk about how we can run, play, and control on top of it.
Thank you, Andre. Hi, everyone. My name is Ashok. I lead the planning and controls, auto labeling, and simulation teams. So, like Andre mentioned, the vision networks take dense video data and then compress it down into a 3D vector space. The role of the planner now is to consume this vector space and get the car to the destination while maximizing the safety, comfort, and the efficiency of the car. Even back in 2019, our planner was pretty capable driver. It was able to stay in the lanes, make lane changes as necessary, and take exits of the highway. But city driving is much more complicated. Rarely there are structured lane lines. Vehicles do much more free-form driving. Then the car has to respond to all of cut-ins and crossing vehicles and pedestrians doing funny things. What is the key problem in planning? Number one, the action space is very non-convex. And number two, it is high-dimensional. What I mean by non-convex is there can be multiple possible solutions that can be independently good, but getting a globally consistent solution is pretty tricky. So there can be pockets of local minima that the planning can get stuck into. And secondly, the high dimensionality comes because the car needs to plan for the next 10 to 15 seconds. It needs to produce the position, velocities, and acceleration over this entire window. This is a lot of parameters to produce at runtime. Discrete search methods are really great at solving non-convex problems because they are discrete, they don't get stuck in local minima, whereas continuous function optimization can easily get stuck in local minima and produce poor solutions that are not great. On the other hand, for high-dimensional problems, discrete search sucks because it is discrete, it does not use any graded information, so literally it has to go and export each point to know how good it is. Whereas continuous optimization uses gradient-based methods to very quickly go to a good solution. Our solution to this entire problem is to break it down hierarchically. First, use a code search method to crunch down the non-convexity and come up with a convex corridor, and then use continuous optimization techniques to make the final smooth trajectory. Let's see an example of how the search operates. So here, we're trying to do a lane change. In this case, the car needs to do 2 back-to-back lane changes to make the left turn up ahead. For this, the car searches over different maneuvers. So in the first one it searches is a lane change that's close by, but the car brakes pretty harshly, so it's pretty uncomfortable. The next maneuver it tries does the lane change a bit late, so it speeds up, goes in front of the other cars, and finally does the lane change. But now it risks missing the left turn. We do thousands of such searches in a very short time span. Because these are all physics-based models, these futures are very easy to simulate, and in the end, we have a set of candidates, and we finally choose one based on the optimality conditions of safety, comfort, and easily making the turn. So now the car has chosen this path, And you can see that as the car executes this trajectory, it pretty much matches what we had planned. The cyan plot on the right side here, that one is the actual velocity of the car, and the white line underneath it was the plan. So we are able to plan for 10 seconds here and able to match that when we see in hindsight. So this is a well-made plan. When driving alongside other agents, it's important to not just plan for ourselves, but instead we have to plan for everyone jointly and optimize for the overall scene's traffic flow. In order to do this, what we do is we literally run the autopilot planner on every single relevant object in the scene. Here's an example of why that's necessary. This is an auto corridor. I'll let you watch the video for a second. Yeah, that was autopilot driving in an auto corridor, going around parked cars, cones, and poles. Here, there's a 3D view of the same thing. The oncoming car arrives now, and autopilot slows down a little bit, but then realizes that we cannot yield to them because we don't have any space to our side. But the other car can yield to us instead. So instead of just blindly braking here, autopilot reasons about that car has low enough velocity that they can pull over and should yield to us because we cannot yield to them, and assertively makes progress. A second oncoming car arrives now. This vehicle has higher velocity, and like I said earlier, we literally run the autopilot planner for the other object. So in this case, we run the planner for them. That object's plan now goes around their side's parked cars, and then after they pass the parked cars, goes back to the right side of the road for them. Since we don't know what's in the mind of the driver, we actually have multiple possible futures for this car. Here, one future is shown in red, the other one is shown as green. The green one is a plan that yields to us. But since this object's velocity and acceleration are pretty high, we don't think that this person is going to yield to us, and they are actually going to go around these parked cars. So autopilot decides that, okay, I have space here. This person is definitely going to come, so I'm going to pull over. So as autopilot is pulling over, we notice that that car has chosen to yield to us based on their yaw rate and their acceleration. And autopilot immediately changes its mind and continues to make progress. This is why we need to plan for everyone, because otherwise we wouldn't know that this person is going to go around the other parked cars and come back to their side. If we didn't do this, autopilot would be too timid and would not be a practical self-driving car. So now we saw how the search and planning for other people set up a convex valley. Finally, we do a continuous optimization to produce the final trajectory that the planner needs to take. Here, the gray thing is the convex corridor, and we initialize a spline in heading and acceleration, parameterized over the arc length of the plan. And you can see that the optimization continuously makes fine-grained changes to reduce all of its costs. Some of the costs, for example, are distance from obstacles, traversal time, and comfort. For comfort, you can see that the lateral acceleration plots on the right have nice trapezoidal shapes. It's going to come up for, yeah, here on the right side, the green plot has a nice trapezoidal shape, and if you record a human trajectory, this is pretty much how it would look like. The lateral jerk is also minimized. So in summary, we do a search for both us and everyone else in the scene. We set up a convex corridor and then optimize for a smooth path. Together, these can do some really neat things like shown above. But driving looks a bit different in other places, like where I grew up from. It's very much more unstructured. Cars and pedestrians cutting each other, harsh braking, honking. It's a crazy world. We can try to scale up these methods, but it's going to be really difficult to efficiently solve this at runtime. What we instead want to do is use learning-based methods to efficiently solve them. And I want to show why this is true. So we're going to go from this complicated problem to a much simpler toy parking problem, but still illustrates the core of the issue. Here, this is a parking lot. The Ego car is in blue, and it needs to park in the green parking spot here. So it needs to go around the curbs, the parked cars, and the cones shown in orange here. Let's do the simple baseline. It's a A-star, it's a standard algorithm that uses a lattice space search. And the heuristic here is the distance, the Euclidean distance to the goal. So you can see that it directly shoots towards the goal, but very quickly gets trapped in a local minima. And it backtracks from there, and then searches a different path to try to go around this parked car. Eventually, it makes progress and gets to the goal, but it ends up using 400,000 nodes for making this. Obviously, this is a terrible heuristic. We want to do better than this. So if you added a navigation route to it and has the car to follow the navigation route while being close to the goal, this is what happens. The navigation route helps immediately, but still, when it encounters cones or other obstacles, it basically does the same thing as before, backtracks and then searches a whole new path. And this poor search has no idea that these obstacles exist. It literally has to go there, check if it's in collision, and if it's in collision, back up. The navigation heuristic helped, but still this took 22,000 nodes. We can design more and more of these heuristics to help the search go faster and faster, but it's really tedious and hard to design a globally optimal heuristic. Even if you had a distance function from the cones that guided the search, this would only be effective for the single cone. But what we need is a global value function. So instead, what we want to use is neural networks to give this heuristic for us. The vision networks produces a vector space, and we have cars moving around in it. This basically looks like an Atari game, and it's a multiplayer version. So we can use techniques such as mu0, alpha0, et cetera, that was used to solve Go and other Atari games to solve the same problem. So we're working on neural networks that can produce state and action distributions that can then be plugged into Monte Carlo tree search with various cost functions. Some of the cost functions can be explicit cost functions like distance to like collisions, comfort, traversal time, et cetera. But they can also be interventions from the actual manual driving events. We trained such a network for this simple parking problem. So here again, same problem. Let's see how MCTS tree search does. So here you notice that the planner is basically able to, in one shot, make progress towards the goal. To notice that this is not even using a navigation heuristic. Just given the scene, the planner is able to go directly towards the goal. All the other offshoots you're seeing are possible options. It's not choosing any of them, just choosing the option that directly takes it towards the goal. The reason is that the neural network is able to absorb the global context of the scene and then produce a value function that effectively guides it towards the global minima as opposed to getting it stuck in any local minima. So this only takes 288 nodes and is several orders of magnitude less than what was done in the A-star with the Euclidean distance heuristic. So this is what a final architecture is going to look like. The vision system is going to crush down the dense video data into a vector space. It's going to be consumed by both an explicit planner and a neural network planner. In addition to this, the network planner can also consume intermediate features of the network. Together, these produce a trajectory distribution, and it can be optimized end-to-end, both with explicit cost functions and human intervention and other imitation data. This then goes into explicit planning function that does whatever is easy for that and produces the final steering and acceleration commands for the car. With that, we need to now explain how we train these networks. And for training these networks, we need large data sets. I invite Andre to speak briefly about manual labeling.
Yeah, so the story of data sets is critical, of course. So far, we've talked only about neural networks, but neural networks only establish an upper bound on your performance. Many of these neural networks, they have hundreds of millions of parameters, and these hundreds of millions of parameters, they have to be set correctly. If you have a bad setting of parameters, this is not going to work. So neural networks are just an upper bound. You also need massive data sets to actually train the correct algorithms inside them. Now, in particular, I mentioned we want data sets directly in the vector space. And so really the question becomes, how can you accumulate, because our networks have hundreds of millions of parameters, how do you accumulate millions and millions of vector space examples that are clean and diverse to actually train these neural networks effectively? Now, so there's a story of data sets and how they've evolved on the side of all of the models and developments that we've achieved. Now, in particular, when I joined roughly 4 years ago, we were working with a third party to obtain a lot of our data sets. Now, unfortunately, we found very quickly that working with a third party to get data sets for something this critical was just not going to cut it. The latency of working with a third party was extremely high, and honestly, the quality was not amazing. And so in the spirit of full vertical integration at Tesla, we brought all of the labeling in-house. And so over time, we've grown more than 1,000-person data labeling org that is full of professional labelers who are working very closely with the engineers. So actually, they're here in the US and co-located with the engineers here in Bay Area as well. And so we work very closely with them. And we also build all of the infrastructure for them from scratch ourselves. So we have a team who we are going to meet later today that develops and maintains all of this infrastructure for data labeling. And so here, for example, I'm showing some of the screenshots of some of the latency, throughput, and quality statistics that we maintain about all of the labeling workflows and the individual people involved and all the tasks and how the numbers of labels are growing over time. So we found this to be quite critical, and we're very proud of this. Now, in the beginning, roughly 3 or 4 years ago, most of our labeling was in image space. And so you can imagine that this is taking quite some time to annotate an image like this, and this is what it looked like, where we are sort of drawing polygons and polylines on top of these single individual images. As I mentioned, we need millions of vector space labels, so this is not going to cut it. So very quickly, we graduated to 3-dimensional or 4-dimensional labeling, where we are directly labeling in vector space, not in individual images. So here what I'm showing is a clip, and you are seeing a very small reconstruction. You're about to see a lot more reconstructions soon, but it's a very small reconstruction of the ground plane on which the car drove, and a little bit of the point cloud here that was reconstructed. And what you're seeing here is that the labeler is changing the labels directly in vector space, and then we are reprojecting those changes into camera images. So we're labeling directly in vector space, and this gave us a massive increase in throughput for a lot of our labels, because you label once in 3D, and then you get to reproject. But even this, we realized, was actually not going to cut it. Because people and computers have different pros and cons. So people are extremely good at things like semantics, but computers are very good at geometry, reconstruction, triangulation, tracking. And so really for us, it's much more becoming a story of how do humans and computers collaborate to actually create these vector space data sets. And so we're going to now talk about auto-labeling, which is some of the infrastructure we've developed for labeling these clips at scale.
Hi again. So even though we have lots of human labelers, the amount of training data needed for training the network significantly outnumbers them. So we try to invest in a massive auto-labeling pipeline. Here's an example of how we label a single clip. A clip is an entity that has dense sensor data, like videos, IMU data, GPS, odometry, etc. These can be 45-second to a minute long. These can be uploaded by our own engineering cars or from customer cars. We collect these clips and then send them to our servers, where we run a lot of neural networks offline to produce intermediate results, like segmentation masks, depth, point matching, etc. This then goes through a lot of robotics and AI algorithms to produce a final set of labels that can be used to train the networks. One of the first tasks we want to label is the road surface. Typically, we can use splines or meshes to represent the road surface, but those are, because of the topology restrictions, are not differentiable and not amenable to producing this. So what we do instead is in the style of neural radiance fields work from last year, which is quite popular. So we use an implicit representation to represent the road surface. Here, we are querying XY points on the ground and asking for the network to predict the height of the ground surface, along with various semantics such as curbs, lane boundaries, road surface, drivable space, etc. So given a single XY, we get a Z. Together, these make a 3D point, and they can be reprojected into all the camera views. So we make millions of such queries and get lots of points. These points are reprojected into all the camera views. We are showing on the top right here one such camera image with all these points reprojected. Now we can compare this reprojected point with the image space prediction of the segmentations. And jointly optimizing this over all the camera views, both across space and time, produces an excellent reconstruction. Here's an example of how that looks like. So here, this is an optimized road surface that reprojects into the 8 cameras that the car has and across all of time. And you can see how it's consistent across both space and time. So a single car driving through some location can sweep out some patch around the trajectory using this technique. But we don't have to stop there. So here, we collected different clips from the same location, from different cars maybe, and each of them sweeps out some part of their road. Cool thing is we can bring them all together into a single giant optimization. So here, these 16 different trips are organized aligned using various features such as road edges, lane lines. All of them should agree with each other and also agree with all of their image space observations. Together, this produces an effective way to label the road surface, not just where the car drove, but also in other locations that it hasn't driven yet. Again, the point of this is not to just build HD maps or anything like that. It's only to label the clips through these intersections. So we don't have to maintain them forever, as long as the labels are consistent with the videos that they were collected at. Optionally, then humans can come on top of this and clean up any noise or add additional metadata to make it even richer. We don't have to stop at just the road surface. We can also arbitrarily reconstruct 3D static obstacles. Here, this is a reconstructed 3D point cloud from our cameras. The main innovation here is the density of the point cloud. Typically, these points require texture to form associations from one frame to the next frame. But here, we are able to produce these points even on textureless surfaces like the road surface or walls. And this is really useful to annotate arbitrary obstacles that we can see in the world. One more cool advantage of doing all of this on the servers offline is that we have the benefit of hindsight. This is a super useful hack because, say, in the car, the network needs to produce the velocity. It just has to use the historical information and guess what the velocity is. But here, we can look at both the history but also the future and basically cheat and get the correct answer of the kinematics, like velocity, acceleration, etc. One more advantage is that we can have like different tracks, but we can stitch them together even through occlusions. Because we know the future, we have future tracks, we can match them and then associate them. So here you can see the pedestrians on the other side of the road are persisted even through multiple occlusions by these cars. This is really important for the planner because the planner needs to know if it saw someone, it still needs to account for them even then they're occluded. So this is a massive advantage. Combining everything together, we can produce these amazing data sets that annotate all of the road texture, all of the static objects, and all of the moving objects, even through occlusions, producing excellent kinematic labels. You can see how the cars turn smoothly, produce really smooth labels. All the pedestrians are consistently tracked. The parked cars have basically zero velocity, so we can also know that they are parked. So this is huge for us. This is one more example of the same thing. You can see how everything is consistent. We want to produce 1 million such labeled clips and train our multicam video networks with such large data set and really crush this problem. We want to get the same view that's consistent that you're seeing here in the car. We started our first exploration of this with the Remove the Radar project. We removed it in a very short time span, I think, within 3 months. In the early days of the network, we noticed, for example, in low visibility conditions, the network can suffer understandably because obviously this truck just dumped a bunch of snow on us and it's really hard to see. But we should still remember that this car was in front of us. But our networks early on did not do this because of the lack of data in such conditions. So what we did, we asked the fleet to produce lots of similar clips, and the fleet responded, it did. So it produces it produces lots of video clips where shit's falling out of all other vehicles. And we send this through our auto labeling pipeline that was able to label 10K clips within a week. This would have taken several months with humans labeling every single clip here. So we did this for 200 different conditions, and we were able to very quickly create large data sets, and that's how we were able to remove this. So once we train the networks with this data, you can see that it's totally working and keeps in memory that this object was there and provides this. So finally, we wanted to actually get a Cybertruck into a data set for the Remove the Radar. Can you all guess where we got this clip from? I'll give you a moment. Someone said it. Yes, it's rendered. It's our simulation. It was hard for me to tell initially, and if I may say so myself, it looks pretty. It looks very pretty. So yeah, in addition to auto labeling, we also invest heavily in using simulation for labeling our data. So this is the same scene as seen before, but from a different camera angle. So a few things that I wanted to point out, for example, the ground surface. It's not plain asphalt. There are lots of cars and cracks and tar seams. There's some patchwork done on top of it. Vehicles move realistically. The truck is articulated, even goes over the curb and makes a wide turn. The other cars behave smartly. They avoid collisions, go around cars, and also smooth and accelerate smoothly, brake and accelerate smoothly. The car here with the logo on the top is Autopilot. Actually, Autopilot is driving that car, and it's making an unprotected left turn. And since this is simulation, it starts from the vector space. So it has perfect labels. Here we show a few of the labels that we produce. These are vehicle cuboids with kinematics, depth, surface normals, segmentation. But Andre can name a new task that he wants next week, and we can very quickly produce this because we already have the vector space, and we can write the code to produce these labels very, very quickly. So when does simulation help? It helps, number one, when the data is difficult to source. As large as our fleet is, it can still be hard to get some crazy scenes, like this couple and their dog running on the highway while there are other high-speed cars around. This is a pretty rare scene, I'd say, but still can happen, and autopilot still needs to handle it when it happens. When data is difficult to label, there are hundreds of pedestrians crossing the road. This could be a Manhattan, downtown, people crossing the road. It's going to take several hours for humans to label this clip. And even for automatic labeling algorithms, this is really hard to get the association right, and it can produce like bad velocities. But in simulation, this is trivial because you already have the objects. You just have to like spit out the cuboids and the velocities. And also, finally, when we introduce closed-loop behavior, where the car needs to be in a determined situation or the data depends on the actions, this is pretty much the only way to get it reliably. All this is great. What's needed to make this happen? Number one, accurate sensor simulation. Again, the point of the simulation is not to just produce pretty pictures. It needs to produce what the camera in the car would see and other sensors would see. So here, we are stepping through different exposure settings of the real camera on the left side and the simulation on the right side. We're able to pretty much match what the real cameras do. In order to do this, we had to model a lot of the properties of the camera in our sensor simulation, starting from sensor noise, motion blur, optical distortions, even headlight transmissions, even like diffraction patterns of the windshield, etc. We don't use this just for the autopilot software. We also use it to make hardware decisions such as lens design, camera design, sensor placement, even headlight transmission properties. Second, we need to render the visuals in a realistic manner. You cannot have what in the game industry called jaggies. These are aliasing artifacts that are a dead giveaway that this is simulation. We don't want them. So we go through a lot of paints to produce nice spatiotemporal anti-aliasing. We also are working on neural rendering techniques to make this even more realistic. Yeah, in addition, we also use ray tracing to produce realistic lighting and global illumination. Okay, that's the last of the cop cars, I think. We obviously cannot have really just 4 or 5 cars because the network will easily overfit because it knows the sizes. So we need to have realistic assets, like the moose on the road here. We have thousands of assets in our library, and they can wear different shirts and actually can move realistically. So this is really cool. We also have a lot of different locations mapped and created to create these sim environments. We have actually 2,000 miles of road built, and this is almost the length of the roadway from the east coast to the west coast of the United States, which I think is pretty cool. In addition, we have built efficient tooling to build several miles more on a single day for a single artist. But this is just tip of the iceberg. Actually, most of the data that we use to train is created procedurally using algorithms as opposed to artists making these simulation scenarios. So these are all procedurally created roads with lots of parameters such as curvature, varying trees, cones, poles, cars with different velocities, and the interaction produce an endless stream of data for the network. But a lot of this data can be boring because the network may not already get it correct. So what we do is we use also ML-based techniques to basically perturb the network to see where it's failing at and create more data around the failure points of the network. So this is in closed loop trying to make the network performance be better. We don't want to stop there. So actually we want to recreate any failures that happens to the autopilot in simulation so that we can hold autopilot to the same bar from then on. So here on the left side, you're seeing a real clip that was collected from a car. It then goes through our auto labeling pipeline to produce a 3D reconstruction of the scene along with all the moving objects. With this combined with the original visual information, we recreate the same scene synthetically and create a simulation scenario entirely out of it. So, and then when we replay autopilot on it, autopilot can do entirely new things, and we can form new worlds, new outcomes from the original failure. This is amazing because we really don't want autopilot to fail, and when it fails, we want to capture it and keep it to that bar. Not just that, we can actually take the same approach that we said earlier and take it one step further. We can use neural rendering techniques to make it look even more realistic. So we take the original video clip, recreate a synthetic simulation from it, and then apply neural rendering techniques on top of it, and it produces this, which looks amazing in my opinion, because this one is very realistic and looks almost like it was captured by the actual cameras. These are results from last night because it was cool and we wanted to present it. But yeah, yeah, I'm very excited for what SIM can achieve. But this is not all bullshit, because networks trained in the car already use simulation data. We used 300 million images with almost 500 million labels, and we want to crush down all the tasks that are going to come up for the next several months. With that, I invite Milan to explain how we scale these operations and really build a label factory and spit out millions of labels.
All right, thanks, Ashok. Hey, everyone, I'm Milan. I'm responsible for the integration of our neural networks in the car and for most of our neural network training and evaluation infrastructure. And so tonight, I'd just like to start by giving you some perspective into the amount of compute that's needed to power this type of data generation factory. And so in the specific context of the push we went through as a team here a few months ago to get rid of the dependency on the radar sensor for autopilot, we generated over 10 billion labels across 2.5 million clips. And so to do that, we had to scale our huge offline neural networks and our simulation engine across thousands of GPUs and just a little bit shy of 20,000 CPU cores. On top of that, we also included over 2,000 actual autopilot full self-driving computers in the loop with our simulation engine. And that's our smallest compute cluster. So I'd like to give you some idea of what it takes to take our neural networks and move them in the car. And so the two main constraints that we're working under here are mostly latency and frame rate, which are very important for safety, but also to get proper estimates of acceleration and velocity of our surroundings. And so the meat of the problem really is around the AI compiler that we write and extend here within the group that essentially maps the compute operations for my PyTorch model to a set of dedicated and accelerated pieces of hardware. And we do that while figuring out a schedule that's optimized for throughput while working under severe SRAM constraints. And so, by the way, we're not doing that just on one engine, but across two engines on the autopilot computer. And the way we use those engines here at Tesla is such that at any given time, only one of them will actually output control commands to the vehicle, while the other one is used as an extension of compute. But those roles are interchangeable, both at the hardware and software level. So how do we iterate quickly together as a group through these AI development cycles? Well, first, we have been scaling our capacity to evaluate our software and neural network dramatically over the past few years. And today, we're running over 1 million evaluations per week on any code change that the team is producing. And those evaluations run on over 3,000 actual full self-driving computers that are hooked up together in a dedicated cluster. And so on top of this, we've been developing really cool debugging tools. And so here is a video of one of our tools, which is helping developers iterate through the development of neural networks and comparing live the outputs from different revisions of a same neural network model as we're iterating live through video clips. And so last but not least, we've been scaling our neural network training compute dramatically over the past few years. And today, we're barely shy of 10,000 GPUs, which, just to give you some sense, in terms of number of GPU, is more than the top 5 publicly known supercomputers in the world. But that's not enough, and so I'd like to invite Ganesh to talk about the next steps.
Thank you, Milan. My name is Ganesh, and I lead Project Dojo. It's an honor to present this project on behalf of the multidisciplinary Tesla team that is working on this project. As you saw from Milan, there's an insatiable demand for speed as well as capacity for neural network training. And Elon prefetched this, and a few years back, he asked us to design a super fast training computer, and that's how we started Project Dojo. Our goal is to achieve best AI training performance and support all these larger, more complex models that Andre's team is dreaming of, and be power efficient and cost effective at the same time. So we thought about how to build this, and we came up with a distributed compute architecture. After all the training computers out there are distributed computers in one form or the other. They have compute elements in the box out here connected with some kind of network. In this case, it's a two-dimensional network, but it could be any different network. CPU, GPU, accelerators, all of them have compute, little memory, and network. But one thing which is common trend amongst this is it's easy to scale the compute. It's very difficult to scale up bandwidth and extremely difficult to reduce latencies. And you'll see how our design point catered to that, how our philosophy addressed these aspects of traditional limits. For Dojo, we envisioned a large compute plane filled with very robust compute elements backed with large pool of memory and interconnected with very high bandwidth and low latency fabric and in a 2D mesh format. And onto this, for extreme scale, big neural networks will be partitioned and mapped to extract different parallelism, model, graph, data parallelism. And then a neural compiler of ours will exploit spatial and temporal locality such that it can reduce communication footprint to local zones and reduce global communication. And if we do that, our bandwidth utilization can keep scaling with the plane of compute that we desire out here. We wanted to attack this all the way, top to bottom of the stack, and remove any bottlenecks at any of these levels. And let's start this journey in an inside-out fashion, starting with the chip. As I described, chips have compute elements. Our smallest entity of scale is called a training node. And the choice of this node is very important to ensure seamless scaling. If you go too small, it will run fast, but the overheads of synchronization and software will dominate. If you pick it too big, it will have complexities in implementation in the real hardware and ultimately run into memory bottleneck issues. Because we wanted to address latency and bandwidth as our primary optimization point. Let's see how we went about doing this. What we did was we picked the farthest distance a signal could traverse in a very high clock cycle, in this case, 2 gigahertz plus. And we drew a box around it. This is the smallest latency that a signal can traverse, one cycle at a very high frequency. And then we filled up the box with wires to the brink. This is the highest bandwidth you can feed the box with. And then we added machine learning compute underneath, and then a large pool of SRAM. And last but not the least, a programmable core to control. And this gave us our high-performance training node. What this is a 64-bit superscalar CPU optimized around matrix multiply units and vector SIMD. It supports floating point 32, bfloat 16, and a new format, CFP8, configurable FP8. And it is backed by 1.25 megabyte of fast ECC-protected SRAM and the low latency, high bandwidth fabric that we designed. This might be our smallest entity of scale, but it packs a big punch. More than 1 teraflop of compute in our smallest entity of scale. So let's look at the architecture of this. The computer architects out here may recognize this. This is a pretty capable architecture as soon as you see this. It is a superscalar in-order CPU with 4 wide vector and 2 wide scalar and 2 wide vector pipes. We call it in order, although the vector and the scalar pipes can go out of order, but for the purists out there, we still call it in order. And it also has 4-way multi-threading. This increases utilization because we could do compute and data transfers simultaneously. And our custom ISA, which is the instruction set architecture, is fully optimized for machine learning workloads. It has features like transpose, gather, link traversals, broadcast, just to name a few. And even in the physical realm, we made it extremely modular, such that we could start abutting these training nodes in any direction and start forming the compute plane that we envisioned. When we click together 354 of these training nodes, we get our compute array. It's capable of delivering 362 teraflops of machine learning compute. And of course, the high bandwidth fabric that interconnects these. And around this compute array, we surrounded it with high-speed, low-power SerDeses, 576 of them, to enable us to have extreme I/O bandwidth coming out of this chip. Just to give you a comparison point, this is more than 2 times the bandwidth coming out of the state-of-the-art networking switch chips which are out there today. And network switch chips are supposed to be the gold standards for I/O bandwidth. If we put all of it together, we get training optimized chip, our D1 chip. This chip is manufactured in 7 nanometer technology. It packs 50 billion transistors in a miserly 645 millimeter square. One thing you'll notice, 100% of the area out here is going towards machine learning training and bandwidth. There is no dark silicon, there is no legacy support. This is a pure machine learning machine. And this is the D1 chip in a flip chip BGA package. This was entirely designed by Tesla team internally, all the way from the architecture to GDS out and package. This chip is like a GPU level compute with a CPU level flexibility and twice the network chip level I/O bandwidth. If I were to plot the I/O bandwidth on the vertical scale versus teraflops of compute that is available in the state-of-the-art machine learning chips out there, including some of the startups, you can easily see why our design point excels beyond par. Now that we had this fundamental physical building block, how to design the system around it? Let's see. Since D1 chips can seamlessly connect without any glue to each other, we just started putting them together. We just put 500,000 training nodes together to form our compute plane. This is 1,500 D1 chips seamlessly connected to each other. And then we add Dojo interface processors on each end. This is the host bridge to typical hosts in the data centers. It's connected with PCI Gen 4 on one side with a high bandwidth fabric to our compute plane. The interface processors provide not only the host bridge, but high bandwidth DRAM shared memory for the compute plane. In addition, the interface processors can also allow us to have a higher radix network connection. In order to achieve this compute plane, we had to come up with a new way of integrating these chips together. And this is what we call as a training tile. This is the unit of scale for our system. This is a groundbreaking integration of 25 known good D1 dies onto a fan-out wafer process, tightly integrated such that it preserves the bandwidth between them. The maximum bandwidth is preserved there. And in addition, we generated a connector, a high bandwidth, high density connector that preserves the bandwidth coming out of this training tile. And this tile gives us 9 petaflops of compute with a massive I/O bandwidth coming out of it. This perhaps is the biggest organic MCM in the chip industry, multi-chip module. It was not easy to design this. There were no tools that existed. All the tools were croaking. Even our compute cluster couldn't handle it. Our engineers came up with different ways of solving this. They created new methods to make this a reality. Now that we had our compute plane tile with high bandwidth IOs, we had to feed it with power. And here, we came up with a new way of feeding power vertically. We created a custom voltage regulator module that could be reflowed directly onto this fan-out wafer. So what we did out here is we got chip, package, and we brought PCB-level technology of reflow onto this fan-out wafer technology. This is a lot of integration already out here. But we didn't stop here. We integrated the entire electrical, thermal, and mechanical pieces out here to form our training tile fully integrated, interfacing with a 52-volt DC input. It's unprecedented. This is an amazing piece of engineering. Our compute plane is completely orthogonal to power supply and cooling. That makes high bandwidth compute planes possible. What it is a 9 petaflop training tile. This becomes our unit of scale for our system. And this is real. I can't believe I'm holding 9 petaflops out here. And in fact, last week, we got our first functional training tile. And on a limited cooling benchtop setup, we got some networks running. And I was told Andre doesn't believe that we could run networks till we could run one of his creations. Andre, this is MinGPT-2 running on Dojo. Do you believe it? Next up, how to form a compute cluster out of it. By now, you must have realized our modularity story is pretty strong. We just put together some tiles. We just tiled together tiles. A 2x3 tile in a tray makes our training matrix, and 2 trays in a cabinet give 100 petaflops of compute. Did we stop here? No. We just integrated seamlessly. We broke the cabinet walls. We integrated these tiles seamlessly all the way through, preserving the bandwidth. There's no bandwidth divot out here. There's no bandwidth cliffs. All the tiles are seamlessly connected with the same bandwidth. And with this, we have an exapod. This is 1 exaflop of compute in 10 cabinets. It's more than 1 million training nodes that you saw. We paid meticulous attention to that training node, and there are 1 million nodes out here with uniform bandwidth. Not just the hardware, the software aspects are so important to ensure scaling. And not every job requires a huge cluster, so we planned for it right from the get-go. Our compute plane can be subdivided, can be partitioned into units called Dojo processing unit. A DPU consists of 1 or more D1 chips. It also has our interface processor and 1 or more hosts. And this can be scaled up or down as per the needs of any algorithm, any network running on it. What does the user have to do? They have to change their scripts minimally. And this is because of our strong compiler suite. It takes care of fine-grained parallelism and mapping the problems of mapping the neural networks very efficiently onto our compute plane. Our compiler uses multiple techniques to extract parallelism. It can transform the networks to achieve not only fine-grained parallelism using data model graph parallelism techniques, it also can do optimizations to reduce memory footprints. One thing, because of our high bandwidth nature of the fabric is enabled out here, is model parallelism could not have been extended to the same level as what we can. It was limited to chip boundaries. Now we can, because of our high bandwidth, we can extend it to training tiles and beyond. Thus, large networks can be efficiently mapped here at low batch sizes and extract utilization and new levels of performance. In addition, our compiler is capable of handling high-level dynamic control flows like loops, if then else, etc. And our compiler engine is just part of our entire software suite. The stack consists of an extension to PyTorch that ensures the same user-level interfaces that ML scientists are used to. And our compiler generates code on the fly such that it could be reused for subsequent execution. It has a LLVM backend that generates the binary for the hardware. And this ensures we can create optimized code for the hardware without relying on even single line of handwritten kernel. Our driver stack takes care of the multi-host, multi-partitioning that you saw a few slides back. And then we also have profilers and debuggers in our software stack. So with all this, we integrated in a vertical fashion. We broke the traditional barriers to scaling. And that's how we got modularity up and down the stack to add to new levels of performance. To sum it all, this is what it will be. It'll be a fastest AI training computer, 4x the performance at the same cost, 1.3x better performance per watt, that is energy saving, and 5x smaller footprint. This will be Dojo Computer. And we are not done. We are assembling our first cabinets pretty soon, and we have a whole next generation plan already. We are thinking about 10x more with different aspects that we can do, all the way from silicon to the system again. We will have this journey again. We're recruiting heavily for all of these areas. Thank you very much. And next up, Elon will update us on what's beyond our vehicle fleet for AI.
Thank you. Now, unlike Dojo, obviously that was not real. So Dojo is real. The Tesla bot will be real. Basically, if you think about what we're doing right now with the cars, Tesla is arguably the world's biggest robotics company because our cars are like semi-sentient robots on wheels. And with the full self-driving computer, essentially the inference engine on the car, which will keep evolving, obviously, and Dojo, and all the neural nets recognizing the world, understanding how to navigate through the world, it kind of makes sense to put that onto a humanoid form. And we're also quite good at sensors and batteries and actuators. So we think we'll probably have a prototype sometime next year that basically looks like this. And it's intended to be friendly, of course, and navigate through a world built for humans and eliminate dangerous, repetitive, and boring tasks. We're setting it such that it is, at a mechanical level, at a physical level, you can run away from it. And most likely overpower it. So hopefully that doesn't ever happen, but you never know. So it'll be a light, yeah, anyway, 5 miles an hour. If you can run faster than that, it'll be fine. So yeah, it's around 5'8". Has sort of a screen where the head is for useful information, but it's otherwise basically got the autopilot system in it. So it's got cameras, got 8 cameras, and yeah. Full self-driving computer, and making use of all of the same tools that we use in the car. So, I mean, things that I think that are really hard about having a useful humanoid robot is, can it navigate through the world without being explicitly trained? I mean, without explicit, like, line-by-line instructions. Can you talk to it and say, please pick up that bolt and attach it to the car with that wrench, and it should be able to do that. It should be able to, please go to the store and get me the following groceries, that kind of thing. So, yeah, I think we can do that. And yeah, this I think will be quite profound, because if you say, like, what is the economy? It is, at the foundation, it is labor. So what happens when there is, no shortage of labor? This is why I think long term that there will need to be universal basic income. Yeah. But not right now, because this robot doesn't work. So we just need a minute. So yeah, but I think it's essentially in the future, physical work will be a choice. If you want to do it, you can, but you won't need to do it. And yeah, I think it obviously has profound implications for the economy, because given that the economy at its foundational level is labor, I mean, capital equipment is just distilled labor, then is there any actual limit to the economy? Maybe not. So, yeah. Join our team and help build this. All right, so I think we'll have everyone come back on the stage, and you guys can ask questions if you'd like. Yeah. think we got it. All right, cool. If you guys can join me back on stage. I just like maybe try to get the camera angle from there, not from the side. Thanks. All right, cool. So we can probably turn the lights back on. And yeah, great. So we're happy to answer any questions you have about anything on the software, hardware side, where things are going, and yeah, fire away. We have, because the lights are like interrogation lights, we actually cannot see. There we go. Great. Oh, yeah. All right, cool.
I can just, okay, there we go. First off, I mean, thanks to all the presenters. That was just super cool to see everything. I'm just curious at a high level, and this is kind of a question for really anyone who wants to take it. To what extent are you interested in publishing or open sourcing anything that you do for the future?
Well, I mean, it is fundamentally extremely expensive to create the system, so somehow that has to be paid for. I'm not sure how to pay for it if it's fully open sourced. Yeah, unless people want to work for free. But I should say that this is, if other car companies want to license it and use it in their cars, that would be cool. This is not intended to be just limited to Tesla cars.
Is for the Dojo supercomputer. So did you solve the compiler problem of scaling to these many nodes, or if it is solved, is it only applicable to Dojo? Because I'm doing research in deep learning accelerators, and getting the correct scalability or the distribution, even in one chip, is extremely difficult from the research project's perspective. So I was just curious.
Excuse me, mic for Bill. You want to?
Have we solved the problem? Not yet. Are we confident we will solve the problem? Yes. We have demonstrated networks on prototype hardware now. We have models, performance models showing the scaling. The difficulty is, as you said, how do we keep the localities? If we can do enough model parallel, enough data parallel to keep most of the things local, we just keep scaling. We have to fit the parameters in our working set in our SRAM that we have, and we flow through the pipe. There's plenty of opportunities. Sorry, as we get further scale for further processor nodes, have more local memory trade-offs with bandwidth, we can do more things. But as we see it now, the applications that Tesla has, we see a clear path.
And our modularity story means we can have different ratios, different aspects created out of it. I mean, this is something that we chose for our applications internally.
Sure.
I was just saying that the locality portion of it, given that training is such a soft scaling application, even though you have all this compute and have a high bandwidth interconnect, it could not give you that performance because you are doing computations on limited memory at different locations. So I was that's very curious to me when you said it's solved, because I just jumped onto the opportunity and would love to know more, given that how much you can open source.
Right in there.
Yeah.
Yeah, I guess the proof's in the pudding. So we should have Dojo operational next year, and I think we'll obviously use it for training, video training. I mean, fundamentally, this is about like the primary application initially is we've got vast amounts of video, and how do we train vast amounts of video as efficiently as possible, and also shorten the amount of time. Like if you're trying to train to a task, like just in general, innovation is how many iterations and what is the average progress between each iteration. And so if you can reduce the time between iterations, the rate of improvement is much better. So if it takes like sometimes a couple days for a model to train versus a couple hours, that's a big deal. But the acid test here, and what I've told the Dojo team is, like, it's successful if the software team wants to turn off the GPU cluster. But if they want to keep the GPU cluster on, it's not successful. So, yeah.
Hi, Brett over here. Love the presentation. Thank you for getting us out here. Love everything, especially the simulation part of the presentation. I was wondering, it looked very, very, very realistic. Are there any plans to maybe expand simulation to other parts of the company in any way?
Hi, I'm Ian Glow. I manage the autopilot simulation team. So as we go down the path to full self-driving, we're going to have to simulate more and more of the vehicle. Currently, we're simulating vehicle dynamics, but we're going to need BMS, we're going to need the MCU, we're going to need every single part of the vehicle integrated. And that actually makes the autopilot simulator really useful for places outside of autopilot. So I want to expand, or we want to expand eventually to being a universal simulation platform. But I think before that, we're going to be spinning up a lot of Optimus support. And then a little bit further down the line, we have some rough ideas on potentially how to get the simulation infrastructure and some of the cool things we've built into the hands of people outside of the company.
Optimus is the code name for the Tesla bot.
Oops.
Optimus subprime.
Hi, this is Ali Jahanian. Thank you for the great presentation and putting all of these cool things together. Yeah, for a while I have been thinking that the car is already a robot. So why not a humanoid robot? And I'm so happy that today you mentioned that you are going to build such a thing. Especially, I think that this can give opportunity for ways of putting multi-modality together. For instance, we know that in the example that you showed that there was a dog and with some passengers or running together. The language and symbolic processing can really help for visualizing that. So I was wondering if I could hear a little more about this type of putting modalities together, including language and vision, because I have been working with, for instance, mini GPT that Andre put out there. And yeah, I didn't hear much about other modalities that's going into the car, or at least in the simulation. Is there any comment that you could tell us?
Well, driving is fundamentally basically almost entirely vision neural nets. Basically, it's running on a biological vision neural net, and what we're doing here is a silicon camera neural net. So there is some amount of audio. You want to hear if there's like emergency vehicles, or I guess converse with the people in the car. If somebody's yelling something at the car, the car needs to understand what that is. All the things that are necessary for it to be fully autonomous. Yeah. Thank you.
Hi, thank you for all the great work that you've shown. My question is for the team, because the data that was shown seems to be predominantly from the United States that the FSD computer is being trained on. But as it gets rolled out to different countries, which have their own road systems and challenges that come with it, how do you think that it's going to scale? Like I'm assuming like ground up is not a very viable solution. So how does it transfer to different countries?
Well, we actually do train on using data from probably like 50 different countries, but we have to pick. As we're trying to advance full self-driving, we need to pick one country, and since we're located here, we pick the US. And then we get a lot of questions like, why not even Canada? I'm like, well, because the roads are a little different in Canada, different enough. And so when trying to solve a hard problem, you want to say like, okay, what's the, let's not add additional complexity right now. Let's just solve it for the US, and then we'll extrapolate to the rest of the world. But we do use video from all around the world.
Yeah, I think a lot of what we are building is very country agnostic. Fundamentally, all the computer vision components and so on don't care too much about country-specific sort of features. Different countries have roads, and they have curbs, and they have cars, and everything we're building is fairly general for that.
Yeah, and there's the prime directive is don't crash.
Right, and that's true for every country.
Yes, this is the prime directive. I mean, even right now, the car is pretty good at not crashing. And so just basically, whatever it is, don't hit it. Even if it's a UFO that crash landed on the highway, and still don't hit it. You should not need to recognize it in order to not hit it. So that's very important.
And I want to ask that when you do the photometric process, multi-view geometry, how much of an error do you see? Is it like 1 millimeter, 1 centimeter? So if it's not confidential.
Sorry, the question, what is the resolution?
What's the difference between the synthetic? Sure. What is the difference between the synthetically created geometry to the actual geometry?
Yeah, it's usually within a couple centimeters, 3 or 4 centimeters. That's the standard deviation.
With different kind of modalities to bring down that error.
We primarily try to find scalable ways to label. In some occasions, we use other sensors to help benchmark, but we primarily try to use cameras for this system.
Okay, thanks.
Yeah, I mean, I think we want to aim for the car to be positioned accurately to the sort of centimeter level, something on that order.
Obviously, it will depend on distance. Like close-by things can be much more accurate than farther away things, and they would matter less because the car doesn't have to make decisions much farther away. And as it comes close, it will become more and more accurate.
Exactly. A lot of questions.
Thanks, everybody. My question has to do with sort of AI and manufacturing. It's been a while since we've heard about the alien dreadnought concept. Is the humanoid that's behind you guys, is that kind of brought out of the production hell timeline and saying that humans are underrated in that process?
Well, sometimes like something that I say is taken to too much of an extreme. There are parts of the Tesla system that are almost completely automated. And then there are some parts that are almost completely manual. If you were to walk through the whole production system, you would see a very wide range from, like I said, fully automatic to almost completely manual. But the vast majority, most of it is already automated. And then with some of the design architecture changes, like going to large aluminum high-pressure die-cast components, we can take the entire rear third of the car and cast it as a single piece. And now we're going to do the front third of the car as a single piece. So the body line drops by like 60 to 70% in size. But yeah, the robot is not prompted by specifically by manufacturing needs. It's just that we're just obviously making the pieces that are needed for a useful humanoid robot. So I guess we probably should make it. And if we don't, someone else will. And so I guess we should make it and make sure it's safe. I should say, like, also manufacturing, volume manufacturing is extremely difficult and underrated, and we've gotten pretty good at that. So it's also important for the humanoid robot. Like, how do you make the humanoid robot not be super expensive? And
Hi. Thank you for the presentation. And my question will be about scaling of Dojo. And in particular, how do you scale the compute nodes in terms of thermals and power delivery? Because there is only so much heat that you can dispense and only so much power that you can bring to like cluster rack. And how do you plan to scale it? And how do you plan to scale it in multiple data centers?
Sure. You want to take it? Oh, there.
Yeah, hi. I'm Bill. One of the Dojo engineers. So from a thermal standpoint and power standpoint, we've designed it very modular. So what you saw on the compute tile, that will cool the entire tile. So once we hook it up to, it is liquid cooled on both the top and the bottom side. It doesn't need anything else. And so when we talk about clicking these together, once we click it to power and once we click it to cooling, it will be fully powered and fully cooled. And all of that is less than a cubic foot.
Yeah, so Tesla has a lot of expertise in power electronics and in cooling. So we took the power electronics expertise from the vehicle powertrain and the sort of the advanced cooling that we developed for the power electronics and for the vehicle and applied that to the supercomputer. Because as you point out, getting heat out is extremely important. It's just really heat limited. So, yeah, so it's funny that like at the compute level, it's operating at less than a volt, which is a very low voltage. There's a lot of amps, so therefore a lot of heat. I squared R is really bites you on the ass.
Hi, my question's also similarly a question of scaling. So it seems like a natural consequence of using, significantly faster training hardware is that you'd be either training models over a lot more data, or you'd be training a lot more complex models, which would be potentially significantly more expensive to run at inference time on the cars. I guess I was wondering, like, if there was a plan to, like, also apply Dojo as something that you'd be using, like, on the self-driving cars, and if so, like, do you foresee additional challenges there?
So as you could see, like Andre's models are not just for cars. Like there are auto labeling models, there are other models that are like beyond car application, but they feed into the car stack. So Dojo will be used for all of those too, not just the car inference part of the training.
Yeah, I mean, the Dojo's first application will be consuming video data for training that would then be run in the inference engine on the car. But, and that I think is an important test to see if it actually is good but is it actually better than GPU cluster or not? But then beyond that, it's basically a generalized neural net training computer. But it's very much optimized to be a neural net. So, CPUs and GPUs, they're not made to be, they're not designed specifically for training neural nets. We've been able to make GPUs especially very efficient for training neural nets, but that was never their design intent. So it's basically, GPUs are still essentially running at neural net training in emulation mode. So with Dojo, we're saying like, okay, let's just ASIC the whole thing. Let's just have this thing it's built for one purpose, and that is neural net training. And just generally, any system that is designed for a specific purpose will be better than one that is designed for a general purpose.
Hey, I had a question here. Hi. So you described two separate systems. One was for vision, the other was for planner and control. Does Dojo allow you to train networks that cross that boundary? And second thing is, if you were able to train such networks, would you have the onboard compute capability in the FSD system to be able to run that under your tight latency constraints? Thanks.
Yeah, I think we should be able to train planner networks on Dojo or any GPUs. It's really invariant to the platform. And I think If anything, once we make this entire thing end-to-end, it will be more efficient than decoding a lot of these intermediate states. So we should be able to run faster if we make the entire thing end-to-end neural networks. We can avoid a lot of decoding of these intermediate states and only decode only essential things required for driving the car.
Yep. Certainly, end-to-endness is the guiding principle behind a lot of the network developments. And over time in the stack, neural networks have taken on more and more functionality. And so we want everything to be trained end-to-end because we see that that works best. But we are building it incrementally. So right now, the interface, there is vector space, and we are consuming it in the planner, but nothing really fundamentally prevents you from actually taking features and eventually fine-tuning end-to-end. So I think that's definitely where this is headed.
Yeah. And the discovery really is like, what are the right architectures that we need to place in the network blocks to make it amenable to that task? So like Andre described, we can place spatial RNNs to help with the perception problem. And now it's just neural network. So similarly for planning, we need to bake in search and optimization into the network architecture. And once we do that, you should be able to do planning very quickly, similar to C++ algorithms.
Okay. Oh, you don't, okay. I think in kind of traditional planning, you had model predictive control and solving convex optimization problems very quickly. And I'd wonder if there's a compute architecture that's more suited for convex optimization or the model predictive control solutions very quickly.
Yeah, 100%. We want to bake in, like I said earlier, we want to bake in these architectures that do, say, model predictive control, but it just like replace some of the blocks with neural networks. Or if we know the physics of it, we can also use physics-based models, part of the neural networks for our pass itself. So we are going to go towards a hybrid system where we will have neural network blocks placed together with physics-based blocks and more neural networks later. So it will be a hybrid stack, and what we know to do well, we place it explicitly, and what the networks are great at, we'll use the networks to optimize this. So it'll be an end-to-end stack with this architecture baked in.
I mean, I do think that so as long as you've got like surround video neural nets for understanding what's going on and can convert the surround video into vector space, then you basically have a video game. And if it's like if you're in Grand Theft Auto or whatever, you can make the cars drive around and pedestrians walk around without crashing. So you can do. You don't have to have a neural net for control and planning, but it's probably ultimately better. But I think you can probably get to. In fact, I'm sure you can get to much safer than a human with control and planning, primarily in C++ with perception, vision in neural nets.
Hi. My question is, we've seen other companies, for example, use reinforcement learning and machine learning to optimize power consumption in data centers and all kinds of other internal processes. My question is Tesla using machine learning within its manufacturing, design, or other engineering processes?
I discourage use of machine learning because it's really difficult. Unless you have to use machine learning, don't do it. It's usually a red flag when somebody says, we want to use machine learning to solve this task. I'm like, that sounds like bullshit. 99.9% of the time, you do not need it. So it's kind of like you reach for machine learning when you need to, but I've not found it to be a convenient, easy thing to do. It's a super hard thing to do. That may change if you've got a humanoid robot that can, understand normal instructions. Generally minimize use of machine learning in the factory.
Hi. Based on your videos from the simulator, it looked like a combination of graphical and neural approaches. I'm curious what the set of underlying techniques that are used for your simulator and specifically for neural rendering, if you can share.
Yeah, so we're doing, at the bottom of the stack, it's just traditional game techniques, just rasterization, real time, very similar to what you'd see in like GTA. On top of that, we're doing real-time ray tracing, And then those results were really hot off the press. I mean, we had that little asterisk at the bottom that was from last night. We're going into the neural rendering space. We're trying out a bunch of different things. We want to get to the point where the neural rendering is the cherry on the top that pushes it to the point where the models will never be able to overfit on our simulator. Currently, we're doing things similar to photorealism enhancement. There's a recent paper enhancing photorealism enhancement. But we can do a lot more than what they could do in that paper because we have way more labeled data, way more compute, and also we have a lot more control over our environments. And we also have a lot of people who can help us make this run at real time. But we're going to try whatever we can do to get to the point where we can train everything just with the simulator if we had to, but we will never have to because we have so much real world data that no one else has. It's just to fill in the little gaps in the real world.
Yeah, I mean, the simulator is very helpful when there's like these rare cases like collision avoidance right before an accident. And then, ironically, the better our cars become at avoiding accidents, the fewer accidents there are, so then our training set is small, so then we have to make them crash in the simulation. So it's like, okay, minimize potential injury to pedestrians and people in the car. You have 5 meters, you're traveling at 20 meters per second. What actions would minimize probability of injury? And we can run that in sim. So, cars driving down the wrong side of the highway, that kind of thing. Happens occasionally, but not that often.
For your humanoid context, I'm wondering if you've decided on what use cases you're going to start with and what the grand challenges are in that context to make this viable.
Well, I think for the Tesla bot, Optimus, it's basically going to start with just dealing with work that is boring, repetitive, and dangerous. Basically, what is the work that people would least like to do?
Hi, so quick question about your simulations. Obviously, they're not perfect right now, so are you using any sort of domain adaptation techniques to basically bridge the gap between your simulated data and your actual real-world data? Because I imagine it's kind of dangerous to just deploy models which are solely trained on simulated data. So maybe some sort of explicit domain adaptation or something. Is that going on anywhere in your pipeline?
So currently, I mean, we're producing the videos straight out of the simulator, the full clips with kinematics and everything, and then we're just immediately training on them, but it's not the entire data set. It's just a small targeted segment, and we only are evaluating based on real-world video. We're paying a lot of attention to make sure we don't overfit, and if we have to start doing fancier things, we will, but currently we're not having an issue with it overfitting on the simulator. We will as we scale up the data, and that's what we're hoping to use neural rendering to bridge that gap, to push that even further out. We've already done things where we're using like the same network as in the car, but retrain it to detect sim versus real to drive our art decisions. And that's actually helped prevent some of these things as well.
Yeah, just to emphasize that overwhelmingly, the data set is the real video from the cars on the actual roads. Nothing's weirder or has more corner cases than reality. It gets really strange out there. But then if we find, say, a few examples of something very odd, and there's some very odd pictures we've seen, then in order to train it effectively, we want to create simulations, say 1,000 simulations that are variants of that quirky thing that we saw, to fill in some important gaps and make the system better. And really, all of this is about, over time, just reducing the probability of a crash or an injury, and it's called the march of 99.9999% safe, you know. And each 9 is an order of magnitude difficulty increase.
Hey all, thanks so much for the presentation. I was curious about the Tesla bot. Specifically, I'm wondering if there are any specific applications that you think the humanoid form factor lends itself to. And then secondary, because of its human form factor, is emotion or companionship at all thought about on the product roadmap at all?
Well, we certainly hope this does not feature in a dystopian sci-fi movie. But you know, like, really, at this point, we're saying like maybe this robot can. We're trying to be as literal as possible. Can it do boring, dangerous, repetitive jobs that people don't want to do? And you know, once we can have it do that, then maybe it can do other things too. But that's the thing that would be really great to have. So it could be your buddy too. I mean, you can buy one and have it be your friend and whatever. I'm sure that people will think of some very creative uses.
So firstly, thanks for the really incredible presentation. My question's on the AI side. So one thing we've been seeing is that with some of these language modeling AIs, we've seen that scaling has just had incredible impacts in their capabilities and what they're able to do. So I was wondering whether you're seeing similar kinds of effects of scaling in your neural networks and your applications.
Absolutely. A bigger network, typically we see it performs better, provided you have the data to also train it with. And this is also what we see for ourselves. Definitely in the car, we have some latency consideration to be mindful of. And so there we have to get creative to actually deploy much, much larger networks. But as we mentioned, we don't only train neural networks for what goes in the car. We have these auto-labeling pipelines that can utilize models of arbitrary size. So in fact, we've trained a number of models that are not deployable, that are significantly larger and work much better because we want 100%, like we want much higher accuracy for the auto-labeling. And so we've done a lot of that, and there we definitely see this trend.
Yeah, the auto-labeling is an extremely important part of this whole situation. Without the auto-labeling, I think we would not be able to solve the self-driving problem.
It's kind of a funny form of distillation where you're using these very massive models plus the structure of the problem to do this reconstruction, and then you distill that into neural networks that you deploy to the car. But we basically have a lot of neural networks and a lot of tasks that are never intended to go into the car.
As time goes on, you get new frames of information. So you really want to make sure your computer is distributed across all the information as opposed to just taking a single frame and hogging on it for, say, 200 milliseconds. You actually have newer frames coming in. So you want to use all of the information and not just use that one frame.
I think one of the things we're seeing is that the car's predictive ability is eerily good. It's really getting better than human in terms of predicting, like you say, like predict what this road will look like when it's out of sight, like it's around the bend, and it predicts the road with very high accuracy, you know, predict pedestrians or cyclists wherever behind, you know, where it just sees a little corner of the bicycle and a little bit through the windows of the bus. And its ability to predict things is going to be much better than humans, like really way beyond.
Right. Yeah, we see this often where we have something that is not visible, but the neural network is making up stuff that actually is very sensible. Sometimes it's eerily good, and you have to you're wondering this is in the training set. And actually in the limit, you can imagine the neural net has enough parameters to potentially remember Earth. So in the limit, it could actually give you the correct answer, and it's kind of like an HD map baked into the weights of the neural net.
Yeah.
I have a question about the design of the Tesla bot. Specifically, how important is it to maintain that humanoid form? To build hands with 5 fingers that also respects the weight limits could be quite challenging. You might have to use cable-driven, and then that also causes all kinds of issues.
I mean, this is just going to be bot version 1. I mean, we'll see. So it needs to be able to do things that people do, and you know, be a generalized humanoid robot. I mean, you could potentially have it give it like 2 fingers and a thumb or something like that. For now, we'll give it 5 fingers and see if that works out okay. It probably will. It doesn't need to be like, have like incredible grip strength, but it needs to be able to work with tools, and carry a bag, that kind of thing.
Hi, thanks a lot for the presentation. So an old professor of mine told me that the thing he disliked a lot about his Tesla was that the autopilot UX didn't really inspire much confidence in the system, especially when like objects are spinning, classifications are flickering. I was wondering, even if you have a good self-driving system, how are you working on convincing Tesla owners, other road users and just the general public that your system is safe and reliable?
Well, I think that's the cars. A while back, cars used to spin. They don't spin anymore. Not in. If you've seen the FSD beta videos, they're pretty solid, and they will be getting more solid.
Yeah, as you add more and more data and train these multi-cam video networks, like these are pretty recent, actually, just like a few months old, and it's still improving. It's not a done product, and that in our minds we can clearly see how this is just going to be like perfect vector space, because why not? All the information is there in the videos. It should produce it given lots of data and good architectures. And this is just an intermediate point in that timeline.
I mean, it's clearly headed to way better than human, without question.
My turn? Oh, hi, here. I was wondering if you could talk a little bit about the short to medium term economics of the bot, I guess. I understand the long-term vision of replacing physical labor, but I also think repetitive, dangerous, and boring tasks tend to not be so highly compensated. And so I just don't see how to reproduce the, start with a supercar and then break into like the lower end of the market. How do you do that for a robot humanoid?
Well, I guess you'll just have to see.
Hello. Hi. I was curious to know how the car AI prioritizes occupant safety versus pedestrian safety, and what thought process goes into like deciding how to bake this into the AI.
Well, I mean, the thing to appreciate is that from the computer standpoint, everything is moving slowly. So to a human, things are moving fast. To the computer, they are not moving fast. So I think this is, in reality, somewhat of a false dichotomy. Not that it will never happen, but it will be very rare. If you think of it like, going the other direction, like rendering, with full ray tracing, neural net enhanced graphics on something like Cyberpunk or any advanced video game, doing 60 frames a second, perfectly rendered. Like, how long would it take a person to even render 1 frame, and without any mistakes? Can't be done. I mean, it would take like a month just to render one frame out of 60 in a second in a video game. It's computers are fast and humans are slow. I mean, for example, on the rocket side, you cannot steer the rocket to orbit. We actually hooked up a joystick to see if anyone could steer the rocket to orbit, but you need to react at roughly 6-7 hertz. People can't do it. Not even that's pretty low. We're talking more like aiming for like 30 hertz type of thing.
Hi, over here, with hardware 3, there's been lots of speculation that with larger nets, it's hitting the limits of what it can provide. How much headroom has the extended compute modes provided, and at what point would hardware 4 be required, if at all?
Well, I'm confident that hardware 3 or the full self-driving computer 1 will be able to achieve full self-driving at a safety level much greater than a human, probably, I don't know, at least 200 or 300% better than a human. Then obviously there will be a future hardware 4 or full self-driving computer 2 which we'll probably introduce with the Cybertruck. So maybe in about a year or so. That is probably, well, they'll be about 4 times more capable, roughly. But it's really just going to be like, can we take it from, say, for argument's sake, 300% safer than a person to 1,000% safer? Just like there are people on the road who, with varying driving abilities, but we still let people drive. You don't have to be the world's best driver to be on the road. So as we see, so yeah. You guys want to say anything? All right.
So are you worried at all, since you don't have any depth sensors on the car, that people might try like adversarial attacks, like printed out photos or something to try to trick the RGB neural network?
Yeah, like what, pull some like Wile E. Coyote stuff, like paint the tunnel on the wall. It's like, oops. We haven't really seen much of that. I mean, for sure, like right now, if you, most likely, if you had like a T-shirt with a T-shirt with like a stop sign on it, which I actually have a T-shirt with a stop sign on it, and then you like flash the car, it will stop. I proved that. But we can obviously, as we see these adversarial attacks, then we can train the cars to, notice that, well, it's actually a person wearing a T-shirt with a stop sign on it, so it's probably not a real stop sign. Yeah.
Hi, my question is about the prediction and the planning. I'm curious, how do you incorporate uncertainty into your planning algorithms? Do you just basically assume, you mentioned that you run the autopilot for all of the other cars on the road. Do you assume that they're all going to follow those rules, or are you accounting for the possibility that, well, they might be bad drivers, for example?
Yeah, we do account for multimodal futures. It's not that we just choose one. We account for, okay, this person can actually do many things. And we use their actual physics and kinematics to make sure that they're not doing a thing that would interfere with us before we act. So if there's any uncertainty, we are conservative and then would yield to them. Of course, there's a limit to this, because if you're too conservative, then it's probably not practical. So at some point, we have to assert. And even then, we make sure that the other person can yield to us and act sensibly.
I should say, before we introduce something into the fleet, we will run it in shadow mode, and we'll see what would this neural net, for example, have done in this particular situation. And then effectively, the drivers are training the net. So if the neural net would have controlled and say veered right, but the person actually went left, and it's like, oh, there was a difference. Why was there that difference?
Yeah, and secondly,
so
we also
all the human drivers are essentially training the neural net as to what is the correct course of action, assuming it doesn't then end up in a crash. Doesn't count in that case.
Yeah, and secondly, we have various estimates of uncertainty like flicker, and when we observe this, we actually say if you're not able to see something, we actually slow down the car to be, again, safe and get more information before acting. Yeah, we don't want to be brazen and just go into something that we don't know about. We only go into places where we know about.
Yeah, yeah. It should be like, aspirationally, the car should be the less it knows, the slower it goes.
Yeah.
Which is
not true at some point, but now it's
should be speed proportionate to confidence.
Thanks for the presentation. So I am curious, appreciate the fact that the FSD is improving, but if you have the ability to improve one component along the AI stack that presented today, whether it is simulation, data collections, planning and control, etc., which one, in your opinion, is going to have the biggest impact for the performance of the full self-driving system?
It's really the area under the curve of these like multiple points, and if you improve anything, it should improve the area.
I mean, the short term, it's arguably, we need all of the nets to be surround video. And so we still have some legacy. This is very short term. Obviously, we're fixing it fast. But there's still some nets that are not using surround video. And I think ideally that all use surround video. Yeah. Maybe. Yeah.
I think a lot of puzzle pieces are there for success. We just need more strong people to also just help us make it work. You know?
That is the actual bottleneck.
So that is the actual bottleneck, I would say, and really one of the reasons that we are putting on this event.
Exactly. Well said, Andre. That there's just a tremendous amount of work to do to make it work. So that's why we need talented people to join and solve the problem.
Thank you for the great presentation. Lots of my questions answered. But one thing is, when imagine that now you have a large amount of data, even unnecessary. How do you consider that, like, there is a forgetting problem in neural networks? Like, how are you considering those aspects? And also, another one, are you considering an online learning or continuous learning? So that maybe each driver can have their version of self-driving software.
I think I know the literature that you're referring to. That's not some of the problems that we've seen, and we haven't done too much continuous learning. We trained the system once, we fine-tuned a few times. That sort of goes into the car. We need something stable that we can evaluate extensively, and then we think that that's good, and that goes into cars. So we don't do too much learning on spot or continuous learning, and don't face the forgetting problem.
But there will be settings that you can say, like, if you are you typically a conservative driver, or do you want to drive fast or slow? You know, it's like I'm late for the airport. Could you go faster than, you know, basically the kind of instructions you'd give to your Uber driver. It's like, I'm late for the flight, please hurry, or take it easy, or whatever your style is. So let's take a few more questions here, and then we'll call it a day.
All right. So as our models have become more and more capable, and I guess you're deploying these models into the real world, one thing I guess that's possible is for AI to become more, I guess, misaligned with what humans desire. So I guess, is that something that you guys are worried about as you guys deploy more and more robots, or do you guys we'll solve that problem when we get there?
Yeah, I think that we should be worried about AI. Now, like, what we're trying to do here is, I'd say, narrow AI, pretty narrow, like just make the car drive better than a human. And then have the humanoid robot be able to do basic stuff. So at the point at which you sort of start to get to superhuman intelligence, I don't know, all bets are off. But and that's that'll probably happen. But what we're trying to do here at Tesla is make useful AI that people love and is unequivocally good. That's our, we'll try to aim for that. Okay, maybe one more question.
Hi, my question is about the camera sensor. In the beginning of the talk, you had mentioned about building a synthetic animal. And if you think about it, a camera is a very poor approximation of a human eye. And a human eye does a lot more than take a sequence of frames. Have you looked into, there are these days are cameras like event cameras. Have you looked into them? Or are you looking into a more flexible camera design or building your own camera, for example?
Well, with Hardware 4, we will have a next generation camera. But I have to say that the current cameras, we have not reached the limit of the current cameras. And I'm confident we can achieve full self-driving with much higher safety than humans with the current cameras and current compute hardware. But it'd be good to be 1,000% better rather than 300% better. So we'll see continued evolution on all levels in pursuit of that goal. And I think in the future, people will look back and say, "Wow, I can't believe we had to drive these cars ourselves." It'll like self-driving cars will just be just a normal, like self-driving elevators. You know, elevators used to have elevator operators, and there's someone there with like, you know, a big relay switch operating the elevator, and then every now and then they'd get tired or, you know, make a mistake and shear somebody in half. So, so now we made elevators automatic, and you just go and you press the button, and you can be in a 100-story skyscraper and don't really worry about it. Just go in and press the button, and the elevator takes you where you want to go. But it used to be that all elevators were operated manually. And it'll be the same thing like for cars. All cars will be automatic. And then, and electric, obviously. So there will still be some gasoline cars and some manual cars, just like there are still some horses. So, all right, well, thanks everyone for coming, and hope you enjoyed the presentation, and thank you for the great questions. All right.
Good evening, ladies and gentlemen. Welcome to Fremont, California. We're out here at the test track of our Fremont factory, just a few meters away from where we actually build all of our Tesla vehicles. We're super excited to have you all here. In fact, almost 9 years ago, on June 22nd, 2012, we had our first Model S delivery event right over there in the factory. So we've come a long way in a few years. We set out to design, engineer, and manufacture the best car in the planet, and we've been working tirelessly every day to try to make that happen. And tonight, we're going to show you the next best version of Model S. And I brought this along because we might be breaking a few records. But more about that later. So let's get Elon out here and have him show you how we made the best car in the world.
The Model S. This is an ambitious goal to create a whole new kind of car. A lot of Wall Street is betting Tesla can't get it done.
All right. Thanks for coming and thanks for tuning in. So, as Franz was saying, this is 9 years since we delivered the first Model S, the first car produced here in Fremont. So almost a decade. And I think we're really taken it to a whole new level with Plaid. Some of you may know that, I mean, basically our product plan is stolen from Spaceballs. So we've gone Plaid speed. So what we really wanted to achieve here is like, well, why make this really fast car that's crazy fast and everything? And I think there is something that's quite important to the future of sustainable energy, which is that we got to show that an electric car is the best car, hands down. So it's got to be clear. It's like, man, this is sustainable energy cars. It can be the fastest cars, can be the safest cars, can be the most kick-ass cars in every way. And that's why we did the Plaid. It's just to show hands down, this is the way to go. So, yes. Pressing slide. There we go. All right. So, we've made huge improvements from the original car. Well, actually, who here, has anyone here, probably some have, bought the early Model S? Like the, yeah. All right. Well, thank you for your support. You can see the huge improvements we've made. So, and it started off with good performance, but now with Plaid, we've managed to break the 2-second barrier, if you will. No production car has ever done 0 to 60 in under 2 seconds. And this is a 4-door car, seats 5 adults, et cetera, et cetera. It's like, this thing's moving. I mean, this is like what I call like limit of physics engineering. It's not relative engineering. It's like, what does physics say we could do? Because physics is the law and everything else is a recommendation. So, in addition to a crazy performance, it's also got a longer range. Even with the tri-motor high performance, it's got almost a 400-mile range. And in the dual motor configuration, it's got a 412-mile range. So, 420, give or take. So, that joke will never end. So, and we've also improved the supercharging speed, so you can get 187 miles of range in 15 minutes. So. Yeah, so quickest production car, to be clear, of any kind ever made, like I said, first to ever break the 2-second barrier. Later tonight, you'll get a chance to drive around the track, and like this is really something you have to feel to believe, because it hits you right in the limbic system. It's like, damn, like, whoa, yeah. It is basically, what is the car that we can, how can we make a spaceship a car, So, hello. Let's see. Yep. And then in terms of additional stats, it's also the fastest production car to complete a quarter mile, so 9.23 seconds. It's got a 200-mile-an-hour top speed, over 1,000 horsepower, almost 400-mile range. Like I said, charges so fast, it'll be probably done by the time you have a coffee, basically. And talking about some of the sort of details behind it. So we have an all-new battery pack. And then something we're really proud of is the new carbon-sleeved rotors for the motor. So this is the first time that to the best of our knowledge, there's been a production electric motor that has a carbon overwrapped rotor. So This is a super hard thing to do because carbon and copper have, have very different rates of thermal expansion. So in order to do a carbon overwrapped rotor, you've got to wind it at extremely high tension. It's a very hard thing to do. We actually had to design the machine that makes the rotor. So no such machine existed before. It also means that we can have the electromagnetic field be super efficient and have a tight gap even at super high RPM. And it's single speed from 0 to 200 miles an hour. So it's just, the RPM is so crazy that just the centrifugal force wants to expand the rotor. So the carbon overwrap actually holds the rotor, basically holds the rotor together. It's like madness. So, yeah. So let's see. In fact, we're going to show you the motor. In fact, you might have had a chance to see the drive unit. And we can go closer. I mean, this is really an amazing work of engineering. Yeah. There's just never been an electric motor like this. I mean, you can pick this motor up with your hands, and it can accelerate a 2-ton car to 60 miles an hour in 2 seconds. I mean, that kind of power to weight is insane. Yeah. So it goes, it goes up to 20,000 RPM and maybe a little more. So we also were able to achieve the lowest drag coefficient of any car ever made. So, yeah. So really, I think Tesla engineering has outdone itself here. This is a car that looks good, but also gets an incredible drag coefficient. And this is the true drag coefficient of the car, including with wheels in motion. Sometimes you'll hear drag coefficients quoted, but that'll be without the wheels moving. And the wheels cause sort of air churn and incremental drag. And this is the actual drag coefficient of the car. So it's to have a good-looking sports car, have that lower drag coefficient is really tough. So we also have the latest and greatest in heat pump, which is basically the HVAC system for the car. It's 30% better cold weather range and requires 50% less energy for cabin heating in freezing conditions. Yeah, so you'll see very little degradation in cold weather. And the radiator is twice as big for heat rejection. So you'll be able to actually do back-to-back 0 to 60s, go on the track, just haul ass, and as you'll see tonight, this car is just going to do over and over again, and it doesn't get winded. I think we got to take this back to maybe the Nürburgring. See what happens. And then, of course, when we first delivered the Model S, there were no superchargers anywhere in the world. So back in 2012, no superchargers anywhere. Now there are 25,000 superchargers all around the world. So, we opened 30 just in the last week. And we're just going to keep going so that you can basically travel anywhere you want with peace of mind, super easy. Keep increasing the power of the superchargers. We're 250 kilowatts, so obviously that we'll start going to 280, 300, 350. Yeah. So. And then it's also engineered for maximum safety as well. So, in fact, this is designed to be our aspiration for this car. It still has to be tested by the US government, but we think we can get the lowest probability of injury of any car ever tested. So, in fact, these are the actual NHTSA probability of injuries numbers. All top 5 cars with the lowest probability of injuries ever tested, all 5 are Teslas. So I mean, with the Plaid Model S, what you have is a car that is faster, than quicker than any sports car, and like faster than any Porsche, safer than any Volvo in the same car. That's insane. It's like, you know, yeah. So, and then the design, we've obviously made a lot of refinements to the exterior, and then we've completely redone the interior. So I think once you drive the new Model S, it really feels like you're driving the future. And other cars are going to, especially like non-Tesla cars, are going to feel very last century. So, all new interior. As you can see, we changed the orientation of the main screen, so it's easier to watch movies and that kind of thing in landscape. Yeah, exactly. I mean, in other notes, we have ventilated front seats. So, yeah. Anyway, I think it's really, you drive around and it really feels like, okay, we're in 2021. Great. We have this yoke steering wheel, which is a little different, but I think once you try it, you'll think it's great. The visibility of the main screen is super clear, especially for autopilot. So you can see the entire panoramic view you can basically see the mind's eye of the car. Yeah, it's really cool. So. And then we've gotten rid of the stalks. So, like, I think generally all input is error. So we want, if you have to do something that the car could have done already, that should be taken care of. The software should just do it. So you can actually just literally walk up to the car, it senses that you're approaching, unlocks the car based on your phone. It just basically pairs with your phone, knows that you're coming to the car, opens the door, extends the handle, you sit down, and you just drive. You don't have to press the drive or anything like that. The car knows you want to drive. It figures like, yeah, good guess, you know. So, and then it's using the autopilot system to know where the obstacles are. So obviously, if there's something in front of you, you want to go backwards, and if there's something in back of you, you want to go front, most likely. And then it will adapt to your to your needs. So if it sees that you're always doing this, you're changing to reverse or forward in particular situations, it'll try to remember that and geocode it to that location. So then you won't have to do it in the future. It will just keep minimizing the amount of input that you need to do until the car just reads your mind. So it's gonna be great. Yeah. So we've redesigned the interior. We moved the interior so that the front IP is actually slimmer and thinner. So we were able to move the front seats forward, giving more room to the back seat, and we reclined the back seat more and reduced the interior trim. So basically, the current Model S, the back seat is not amazing, but the new one, it's actually a legit back seat. I'd say, it's like it's good. So you can. I think it's quite a comfortable back seat, and you've got also a rear screen, and you can control everything from the back. Yeah. So it's got dual inductive chargers for your phones in the back and dual inductive in the front. And it's a 36-watt power supply, so you can actually charge like your, laptop or anything. Basically, it's a 36-watt USB-C. Yeah. It can also pair with multiple Bluetooth devices simultaneously. So multiple people could be controlling music, or somebody could be playing a video game. So you can do multiple wireless things simultaneously. And then, similar to the Model 3 and Y, instead of having air vents, we use intersecting columns of air. So, and we just vary the speed of the air. So you don't have to. There's no vents that you can see. and you can just touch the screen and move the screen around, and it'll just move the air wherever you want it. And the air is much more diffuse. It just feels like an invisible air conditioning system. It's great. So, and it's a tri-zone, so there's a zone for the rear, and a front and left front, right front zone. So. And then the 17-inch touchscreen it feels like a movie theater. The sound is incredible. And yeah, so you can really, it's like a home theater experience. So if you're sitting somewhere waiting, or for whatever reason, or at a supercharger, you can just catch up on what your favorite Netflix show, or iTunes, or whatever the case may be, YouTube. And of course, you can also play video games. So, and the same thing for the rear. So you can, rear, it basically, the system feeds all 3 screens, and so you can do things the front, rear. It's great. We have an all-new sound system designed by Tesla Audio, and we have acoustic glass throughout the car, so the car is very quiet when going down the highway. Even at very high speeds, like you're doing 100 miles an hour, it's still quiet. And this is a Tesla-designed codec, so it will keep uploading improved versions of the sound system. It's completely software-defined, so we'll keep tweaking it and dynamically adjusting to whether you're using streaming, or whether it's coming via Bluetooth from your phone, or different streaming services. It'll actually, and if the data rate changes, it'll adapt that. So basically, it always sounds good. And that's just going to get better. So, yeah. And then we've got an all-new UI. So, really want waypoints. Okay, does everybody here want waypoints? All right, fine, we'll do waypoints. God damn it. All right. 2 weeks. All right, we'll do waypoints, fine. But obviously, it also interfaces with your calendar. So if you just, basically, if you just get in the car, and you just sort of swipe down from Navigate. You don't have to enter anything, just swipe down. The car will automatically figure out if you want to go to home, work, or what's on your calendar. So it'll default to calendar priority, and obviously if you're at home and it's kind of a weekday or whatever, it assumes you're going to go to work. So you just swipe down, automatically navigates to work, and checks traffic and gives you an optimal route. So it's just like a nice little easy thing. And you can actually set it to automatically generate the most probable route. So you just get in, and it's going to guess what route you want, and you don't have to press anything. Yeah. So anyway, the UI is basically easy to move around, expand, contract, shift music to the left, to the right, and we're going to keep improving it. So it basically feels like a modern tablet or phone. And then it's not PS4, it's PS5. So I think there's never been a car that has state-of-the-art computing technology, state-of-the-art infotainment, where this is literally at the level of a PlayStation 5. So, yeah, I mean, if you think about the future where the car is often in autopilot or full self-driving mode, then entertainment is going to become increasingly important. So you're going to want to watch movies, play games, use the internet, just all the things you want to do if you're not driving. And this is actual PlayStation 5 level performance. So we're going to try to do a gaming demo. Yes. It can play Cyberpunk. So this is somebody playing the car right now. This is so playing live. Yeah. So it's like pretty great, So have fun in the game. It's gonna be great. So, all right. So high frame rate will do 60 frames a second with state-of-the-art games. Yeah. All right, so we got incredible performance, interior of the future. I think engineering that's practically alien. So, like I said, simultaneously the safest car in the world and the fastest. This is insane. So, we also got look at some things like the power curve. So I think this really illustrates the difference. It maintains 1,000 horsepower all the way up to 200 miles an hour. This car crushes. All right. So, yes. All right, and deliveries begin now. So we're in production. We're going to deliver the first 25 cars now, and then basically should be at several hundred cars per week soon, and 1,000 cars a week probably next quarter. So please enjoy. We put a lot of work into this. I'd like to thank the incredible work of the Tesla engineering and production teams. So my hat is off to Tesla engineering, production, design, the whole group. They put their heart and soul into this. So hope you enjoy it. So let's deliver some cars. All right. Hey, everyone. Well, I mean, this is definitely a new approach. We got the Tesla drive-in movie theater, basically. It's good to see everyone. It's a little hard to read the room with everyone being in cars, but it's it's the only way we could do it. So hopefully it's cool, and hopefully you can hear me. Can you guys hear me? Okay. All right, great. All right, well, thanks for coming. I think it's been an incredible year, and I'd like to thank you for your support through tough times, good times. It's been great. Really appreciate everyone who's put their hard-earned money into Tesla, and I think it's worked out pretty well. This has been a good year, and I think there's many good years to come. So I'll go through the sort of the shareholder presentation, I think, fairly quickly, because the sort of real main event here is Battery Day. So, really, I'm just going through a recap of what's happened over the past year or so. I think starting from in terms of our ability to create a factory, huge kudos to the Tesla Shanghai team for being able to go from literally a dirt pile to volume production in 15 months. It's like, damn, yeah. So, and I think something that's really quite noteworthy here is Tesla is the only foreign manufacturer to have a 100% owned factory in China. So this is often not well understood or not appreciated, but to have the only 100% owned foreign factory in China is a really big deal, and it's paying huge dividends here. So we really wouldn't have the results that we have had this year without the great efforts of the Tesla China team. So I'm super appreciative of that. And we'll see the Shanghai factory continue to scale quite a bit from where it is right now. I think we really could expect that to be, over time, a factory that produces over 1 million vehicles a year. Yeah, it's cool. So let's see. So we also reached in the past year volume production of the Model Y, and this was the smoothest launch that we've ever had. So I think we're definitely getting better at new vehicle launches and building factories and scaling production. As you've heard me say before, it's the hardest thing is scaling production, especially of a new technology. It's insanely difficult. Making a prototype is relatively easy, and if I think of like what is the real achievement of Tesla in sort of car company terms, it's like it wasn't making sort of exciting prototypes. It was that Tesla was really the first company in about a century in the U.S., the first U.S. company in the U.S. to reach volume production and be sustainably profitable. Like the crazy thing is this has really not happened in 100 years. That's the actual super hard part. And we now have 4 vehicles in volume production, S3, XY. So also the toughest joke, I think maybe ever. It was a very difficult joke to make. So we also introduced the lowest cost solar in the US. It's only $1.49 a watt. And we really just simplified the whole value chain. So reduced sales and advertising, got rid of a bunch of unnecessary costs, and really are just relying upon the fact that it's just the lowest cost, most efficient solar in the US, providing both retrofit and the solar glass roof, which I think is a really great product, a hard product to make work, but it will be a major product line in the future. And we also got 4 consecutive quarters of GAAP profitability, which was very difficult. Yeah. So, and certainly a testament to the hard work of people at Tesla. I mean, to do this in extremely difficult times against a wide range of adverse circumstances was insanely hard, but we got it done. So, and I think the future is looking like I think very promising from sort of an annual profitability standpoint. So, in order to achieve, in order to sort of do well financially, you really need economies of scale, and you need ideally the best technology. And I think we've had the best technology for a while, but now we are also achieving economies of scale. So, and we're also rapidly improving autonomy, which is a massive value add to each car. So, I think the value of Tesla is going to be like total, just on the vehicle side, total vehicles produced times the value of autonomy. That's a way to think about the future value of Tesla. We also have consistent free cash flow generation. This is really important for growth. And a key element here is tightening up the time from when a car is ordered to when it is built and delivered. So for a company that's growing rapidly, it's extremely important to tighten the supply chain and to have, from when parts arrive, put it into a car very quickly and deliver the car very quickly to the customer. And if you can do that inside the sort of your kind of payables timeline, then the faster you grow, the more cash you have. Or conversely, if you're unable to do it within your payables timeline, the faster you grow, the less money you will have, which is obviously bad. It's for a capital-intensive situation. So just tightening up and having the parts move very quickly to the factory, put it in a car, get it to a customer, makes a massive difference to cash flow generation. And I mean, that's why it's extremely important to have a factory in each continent. Because if you don't at least have a factory in the continent, it is impossible to achieve this. So having a factory in China that's able to serve China, and then soon many other countries in the region, will be key to us tightening that total sort of chain of cash flow and getting it, essentially, the faster we grow, the more cash. This is really important. That's also why it's important to have Giga Berlin complete, because then we'll have a factory in China, a factory in the US, and soon a second factory in the US in Austin, and a factory in Europe. And I mean, even for Giga Texas in Austin, even if we had exactly the same costs as in California, it would still be advantageous to do it there because it's roughly 2/3 of the way across the US. So in terms of delivering cars to the central US and to the East Coast, it's just faster, costs less, and it fundamentally improves our economics. So I think this is also maybe something that's not fully appreciated of just how important it is to have a factory at least on the continent or reasonably close to where the end customers is, so you can tighten that whole chain. Industry performance. While the rest of industry has gone down, Tesla has gone up. I think this speaks to, thanks. And so I'd like to thank all the customers for taking a chance on Tesla and buying our product, and really hope you're enjoying it. This is really, our sales, as Al was saying, really grow by word of mouth. So this is really, I think, a very pure, it's very pure in the sense that it's like, it's growing on the basis of existing owners recommending it to new customers. This is really, I think, a good way to grow. And then in 2019, we had 50% growth. And I think we'll do really pretty well in 2020. Probably somewhere between 30 to 40% growth, despite a lot of very difficult circumstances. I mean, there's so many, pandemic, wildfires. It's like a whole bunch of difficult production issues. But thanks to the hard work of the Tesla team and a lot of innovative approaches to overcoming issues, we're able to still see significant growth in one of the most difficult, in fact, I'd say probably the most difficult year of Tesla's existence. So, and we also published our extended impact report. At Tesla, we try very hard to do the right thing. If the right thing does not happen, it's just because we maybe made a mistake or weren't aware of it. But we always try to do the right thing to the best of our ability. And then we published the extended impact report to show, just a sort of a self-examination of, okay, what are we doing right? What are we doing wrong? What can we do better in the future? We're definitely trying to accomplish the most good. And so, if we occasionally make a mistake, we work quickly to fix it and do the right thing. So, it's worth looking at like the average life cycle emissions in the U.S. and just how much better a Tesla is than, or an electric car, than any other, than any kind of gasoline car. And what we'll talk about in the battery day is also just how much the grids around the world, and actually, especially in the US, are greening. It's actually much faster than I think people realize. The US is moving towards sustainable energy. And so as we move more and more to sustainable energy, then effectively you end up building the solar factories and the car factories themselves with solar. Over time you do, or with sustainable energy. Over time you'll even mine with sustainable energy, and eventually it will get to an effective emissions of 0. So that's where things will end up. Yeah. So we also have safety at the core of our design. The Tesla cars are the safest cars ever designed. We have the lowest probability of injury of any cars ever tested by the US government, and that's just passive safety. When you add active safety into that, it's even better. You know, it's really, if safety is important to you, which obviously it is, the safest car you could drive is a Tesla. So, you know, I think some people aren't aware of this, but it's really, safety is paramount. It is actually the #1 design objective when we build a Tesla, is safety. Our factories are also becoming safer, and if you look at the sort of accidents per total vehicle made, it's dramatically better than in the past, and it's already better than industry average, and we're confident we can get it to the best in the auto industry. Autopilot functionality continues to improve, and you can see it in the safety report that we publish every quarter. It's just getting better and better. The U.S. average for collisions is roughly 2.1 per million miles, and with autopilot engaged, it's 0.3. I mean, this is a profound difference. It really massive, and this will get even better. So we're confident that over time we can get the probability of an accident, especially the probability of injury, to 10 times better than the industry average, like an order of magnitude better. So that's just a lot of lives saved and a lot of injuries avoided. So that's a huge priority for us. On the autopilot front, I think it's kind of hard for people to judge the progress of autopilot. Like I'm driving. As a matter of course, I've always done this. I drive the bleeding edge alpha build of autopilot, and so I sort of have insight into what is going on. Previously, about a couple of years ago, we were kind of stuck in a local maximum. So we were improving, but like the improvements kind of started tailing off and just not getting where they needed to be. I call this sort of getting trapped in a local maximum. And so we had to do a fundamental rewrite of the entire autopilot software stack, and all of the labeling software as well. So we're now labeling in 3D video. So this is hugely different from previously, where we were labeling essentially a bunch of single images from the 8 cameras, and they would be labeled at different times by different people. And some of the labels, you literally can't tell what it is you're labeling. So it basically made it sort of, in some cases, impossible to label, and the labels had a lot of errors. Now, with our new labeling tools, we label it in video. So we actually label entire video segments, and the system, so you get basically a surround video thing to label, and with the surround video and with time. So it's now taking all cameras simultaneously, and looking at how the images change over time and labeling that. And then the sophistication of the neural nets in the car and the overall logic in the car has improved dramatically. I think we'll hopefully release a private beta of Autopilot, of the full self-driving version of Autopilot, in I think a month or so, and then people will really understand just the magnitude of the change. It's profound. So yeah. anyway, so you'll see it's just like a hell of a step change. But because we had to rewrite everything, labeling software, just the entire code base, it took us quite a while. And the sort of new sort of, I call it like 4D in the sense that it's 3 dimensions plus time. It's just taken us a while to rewrite everything. And so, you'll see what it's like. It's amazing. Yeah, it's just clearly going to work. Tesla core competencies, we've got engineering, obviously. But also manufacturing. I think manufacturing is underappreciated in general. And the difficulty of designing the machine that makes the machine is vastly harder than the machine itself. So, the designing, like making a Model 3 or Model Y or Cybertruck prototype is really quite trivial compared to designing the factory that makes it. Especially if it's new technology and you want to use new manufacturing methods, it's just at least 10 to 100 times harder to do the factory than the prototype. And that's why you see a lot of companies out there or startups, they'll bring out a prototype, but they just can't get it over the hump for manufacturing, because manufacturing of new technology especially is the hardest thing by far. Like basically the prototype is at best 10% of the difficulty and probably closer to 1%. And then software. Tesla is both a hardware and a software company. So a huge percentage of our engineers are actually software engineers. And you can think of our car as kind of like a laptop on wheels. And so software is incredibly important. And so not just in the car, but also in the factory. So the factory software is extremely important. Just software in general. These are fundamental. These are the 3 critical areas that are needed to make for an awesome company. So, yeah. So we have now we'll soon have 3 new factories, incremental, on, well, we have one already, on 3 different continents. Shanghai, we're expanding the Shanghai with the second phase. Berlin is making rapid progress, and Texas is making even faster progress. So, yeah. With each factory, what we're trying to do is also improve the manufacturing technology. So, it's in some cases, like the Model Y made in Berlin might look the same, but it actually is made in a much more efficient way. And yeah, we'll talk about that later in the battery presentation. Yeah, launched Megapack. It's a 3 megawatt-hours all-in-one energy storage solution. So it's been great overall. Yeah. All right, and I think that's basically it. Right? All right, thank you. All right. Well, thanks everyone for coming, and we'll be back in a little bit to go through the battery stuff. And there's a little bit more, in addition to the battery stuff, we got a few extras as well. So I think you'll really like what we have to say on batteries. The battery stuff we're going to talk about is truly revolutionary and essential to Tesla's goal. The fundamental good of Tesla. It's like if you look back in history and say what good did Tesla do? The good will be to by how many years did we accelerate sustainable energy? That's like the true metric of success. It matters if sustainable energy happens faster or slower, and so that's really like how I think about Tesla and how we should sort of assess our progress. By how many years did we accelerate sustainable energy? And what we're going to talk about with batteries and a few other things will really explain how we're going to make a step change improvement in the acceleration of sustainable energy. Thank you.
Hi, folks. That was great. We're going to take a short break before we begin the Battery Day event. So stay tuned. If you're local and here in the audience today, you can feel free to get out of the cars and stretch your legs. But try to stay near the cars because we're going to begin promptly in a little bit. See you soon.
Hello, everyone. Sure. Thanks, Elon. Oh, hi. I'm Drew Baglino, SVP of Powertrain and Energy Engineering at Tesla, and I'm incredibly excited to talk about what we've been doing at batteries here at Tesla.
Great. So let's see, you got the clicker?
Yeah, I've got the clicker, yeah.
Okay, I'll take it first, perhaps.
Sure.
So obviously the issues we're facing are very serious, with climate change, and we're experiencing these issues on a day-to-day basis. It's incredibly important we accelerate the advent of sustainable energy. Time really matters. This presentation is about accelerating the time to sustainable energy. So the past 5 years were the hottest on record. We have what looks like a wall for CO2 ppm. It's obviously, this time is not like the past. It's really important that we take action. Running this climate experiment is insane. So,
especially when it's just a transitory one anyway.
Yes.
We're going to run out of these fossil fuels. Let's just move to the future and not run this experiment any longer.
Yeah. Maybe talk a bit louder.
You got it.
Okay. So anyway, there is a lot of good news, though. A lot of people may not be aware that wind and solar comprise 75% of new electricity capacity in the U.S. this year. So this is a really major. So the grid is going sustainable very, very quickly. Now it's also worth noting that the length of time that power plants last is on the order of 25 years. So even if 100% of energy generation was sustainable, it would still take 25 years to convert the grid. And it's also worth noting that in the past 10 years, power production from coal has dropped in half. So it went from 46% of electricity in 2010 to 23% in 2020. So this is a massive improvement. So good things are happening on a lot of levels. We just need to go faster. So in terms of Tesla's contribution, we've delivered over 1 million electric vehicles, 26 billion electric miles driven, and many gigawatt hours of stationary batteries, 17 terawatt hours of solar generated. So I think solar is sometimes underweighted at Tesla, but it is a massive part of our future. The three parts of a sustainable energy future are sustainable energy generation, storage, and electric vehicles. So we intend to play a significant role in all three. So to accelerate the transition to sustainable energy, we must produce more EVs that need to be affordable and a lot more energy storage while building factories faster and with far less investment. So goal number one is a terawatt-hour scale battery production. So tera is the new giga, and a terawatt is 1,000 times more than a gigawatt. So we used to talk in terms of gigawatts. In the future, we'll be talking in terms of terawatt hours. So this is what's needed in order to transition the world to sustainability.
Yeah, and you can see we're talking about 100x growth in batteries for electric vehicles to achieve this mission. And we are going to get there. It's just a matter of how fast, and our intention is to accelerate it.
Yeah. You basically need on the order of roughly 10 terawatt hours a year of battery production to transition the global fleet of vehicles to electric.
And the average vehicle lasts 15 years, so we're talking about 150 terawatt hours, give or take, to transition the whole all vehicles of all types to electric.
Yeah, so it's a lot of batteries, basically. Yeah, so.
And then on the grid side, we have a similar mountain to climb, 1,600 times growth from today's grid batteries to go 100% renewable on the grid and to take all of the existing heating fossil fuel uses in homes and businesses 100% electric.
Yeah, and this number, I think, might grow even more, as the world economy matures and as countries with high populations industrialize, we could see this number be even more. But let's say it's like roughly 20 to 25 terawatt hours per year, sustained for 15 to 25 years to transition the world to renewable. This is a lot.
Yeah.
So today's batteries can't scale fast enough. They're just too small. For Giga Nevada, 150 gigawatt hours per year is like what we probably expect to make out of there. But this is really pretty small in the grand scheme of things. That's only 0.15 terawatt hours. And they cost too much. So
we would need 135 fully built out Nevada gigafactories to achieve 20 terawatt hours a year. It's not scalable enough of a solution. We need a dramatic rethink of the cell manufacturing system to scale as fast as we can and should.
yeah, and I think we should view this as more than just a question of money. Money is sort of like an ethereal thing, but it's really the amount of effort. You have a certain amount of effort, in terms of people and machines, and depending on how efficient that effort is, for a given amount of effort, you want the most amount of batteries. So it's not just a question of like, well, if we had $2 trillion, tomorrow you could make this. It's not that easy. You actually need to organize a massive number of people, build a lot of machines, build the machines that make the machines. And so it's incredibly important to have that effort yield the most number of batteries. So, and then goal two, obviously, we need to make more affordable cars. I think one of the things that troubles me the most is that we don't yet have a truly affordable car, and that is something that we will make in the future. But in order to do that, we've got to get the cost of batteries down. We've got to make, and we've got to be better at manufacturing, and we need to do something about this curve. The curve of the cost per kilowatt hour of batteries is not improving fast enough. So we've given this a lot of thought over many years to say, okay, how can we radically improve the cost per kilowatt hour curve? It's been somewhat flattening out, actually, in recent years. So
I mean, early growth was promising, but you can see we're kind of plateauing. So that's what's motivating us to rethink how cells are produced and designed.
Yeah, exactly. And EV market share is growing, but EVs, still aren't accessible to all. And you can see, as Drew was saying, it's like starting to flatten out a little bit because the rate of improvement of the affordability of cars is just not fast enough. So that's why we got Battery Day.
Yeah. To make the best cars in the world, we design vehicles and factories from the ground up. Next.
Yeah.
And now we do this for batteries as well.
Yeah. It's weird, the slides don't show up quite right. Anyway, what shows up on the screen is not quite what shows up there. Anyway.
Oh, okay.
It's different.
Yeah, I think it's because that's,
No, that one's current, supposed to be current. Anyway.
So let's get started. We have a plan to halve the cost per kilowatt hour.
Yeah.
And it's not a plan that rests on a single innovation, some research project that'll never see the light of day. It's a plan that has taken creative engineering and industrialization across every facet of what makes a cell into a battery pack, from raw material to the finished thing. And we're going to go through that plan with you today, step by step, and build up how we get to these goals and how we accelerate this transition and make our vehicles and our grid batteries more affordable.
Yeah. I mean, we basically thought through every element of the battery, well, almost every element. There are a few more elements that we won't get to today, but we will get to in the future.
Yes. So first, before we get too far into it, let's talk about what is in a battery cell. We've got the cap and the can, negative and positive terminals of the cell. When you open that cell, you've got a tab connected to those terminals, what we call the jelly roll, which is the wound electrodes on the inside. You can actually see what this looks like as you unwind it. This is over 1 meter long in a typical 2170 cell. So it's quite a long winding process. And you can see the tab still there. And then to explain what's actually going on here, we've identified we've got anode, cathode, separator, positive and negative terminal. Watch what happens as we, there we go, discharge the cell. Got lithium moving from anode to cathode, and then the reverse. When we charge the cell, anode moving from lithium moving from cathode to anode across the separator. This is the basic of what makes all lithium-ion batteries, whether they're no matter what the form factor is. And when we look at what's happened to date, at least in our products, we've moved from the 18650 form factor to the 2170 form factor through great collaboration with our partners, Panasonic, new partners like LG and CATL, and probably others in the future.
Actually, so a slight note on why is the one called the 18650, although not on the slide, versus the 2170, is that the first two digits refer to the diameter, and the second two digits refer to the length. So that helps explain why are these weird. What's up with these weird numbers? But like nobody could explain to me why there was an extra zero. So I said, like, okay, well, we're deleting the zero that nobody can explain in future form factors. So that's why it's technically it's like the 18650 bizarrely, but going forward it's the 2170 because we just got rid of the extra zero because it's pointless.
And this was a evolutionary step, going from 1865 to 2170, bringing 50% more energy into the cell. But when we look to the ideal cell design, if we were to do it ourselves, we need to go beyond just what we're looking at us in front of us, and study the full spectrum of options. So as you can see, we kind of swept the key figures of merit, how much we can reduce the cost, and how much vehicle range increases as we change the outer diameter of the cell. We found a sweet spot somewhere around 46 millimeters. But it's not just about a bigger form factor. Like anybody could make a bigger form factor.
Any fool could make a bigger form factor. We not any fool.
Yeah, exactly. There are problems as you make cells larger. In fact, supercharging and thermals in general become really challenging as you make bigger cells. And this was the challenge that our team set our sights on to overcome. And we did. We came up with this tabless architecture that maybe you've heard about that basically removes the thermal problem from the equation and allows us to go to the absolute lowest cost form factor and the simplest manufacturing process. And this is what we mean when we talk about tabless. It's kind of a beautiful thing.
That's what these T-shirts mean, but it's very esoteric. It's like nobody could figure it out. But
yeah, we basically took the existing foils, laser patterned them, and enabled dozens of connections into the active material through this shingled spiral you can see, with simpler manufacturing, fewer parts, 50 millimeter versus 250 millimeter electrical path length, which is how we get all the thermal benefits.
Yeah, this is important to appreciate. Like basically the distance that electron has to travel, is just much less. So you actually have a shorter path length in a large tabless cell than you have in the smaller cell with tabs. This is a big deal. So even though the cell is bigger, it actually has more power. The power to weight ratio is actually better than the smaller cell with tabs. This is, again, like this is quite hard to do. So it's nobody's done it before. And it really took a tremendous amount of effort within Tesla engineering to figure out how do we make a friggin' tabless cell and have it actually work and then connect that to the top cap. And it's there's a whole bunch of things that we're keeping a little secret sauce here that we're not telling everything. But
sometimes what's elegant and simple is still hard, and it took us a lot of trials, but we're happy where we ended up.
Yeah, I mean everything's simple in recollection. After you simple, everything it's hard until it's discovered, and then it's simple. So anyway, there's a lot of really cool things going on that enable tabless, and it's really due to a really great engineering team. Drew and the rest of the team have done amazing work in achieving this tabless construction. And it sounds, I think it may sort of sound a bit silly to some people, but this is like, for people that really know cells, this is a massive breakthrough.
For cylindricals to be able to get rid of the tabs dramatically simplifies winding and coating.
Yeah.
And has an awesome thermal and performance benefit.
Yeah, that's just to elaborate on that a bit. It's like when the cell is going through the system, it has to keep stopping where all the tabs are.
Yes.
So you can't do continuous motion production if you have tabs. You have to keep stopping, and then there's a rate at which you can start and stop and accelerate again, and it really slows down the rate of production. And then sometimes you get the tabs wrong, and you also lose a little bit of active area. It's really a huge pain in the ass to have tabs from a production standpoint.
Yes. And so when we put it all together and go to our new 80 millimeter length, 4680, we call this new cell design, we get 5 times the energy with 6 times the power and enable 16% range increase just form factor alone.
Yeah, so when these, yeah, it's pretty great. And just to clarify, when we see these plus the 16% or whatever the percentage range increases, these are the amounts due just to that particular innovation.
Yes.
So we'll list a whole bunch of innovations, and then when you add them up, you get a total improvement in energy density and cost. But these numbers are what refer to just this thing.
Yeah, and I want to stress, this is not just a concept or a rendering. We are starting to ramp up manufacturing of these cells at our pilot 10 gigawatt hour production facility just around the corner.
Yeah. So, yeah. It's a video of some of what's going on in the plant. Now, I mean, to be clear, it will take about a year to reach the 10 gigawatt hour capacity. This is important to appreciate. Like when you build a factory, there's a certain capacity that you design to, and then it takes some period of time to actually achieve that capacity. So I would say it's probably about a year before we get to the 10 gigawatt hour annualized rate with the pilot plant. And this is just a pilot plant. The actual production plants will be more on the order of maybe 200 gigawatt hours, maybe more over time.
And thank you. But let's stack up everything we just saw at the cell level. So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change. And now that you've been teased on this factory, we're going to go on and walk step by step through that factory and discuss a series of innovations there. When thinking about the ideal cell factory, we have inspirations behind us in the paper and bottling industry, where from humble beginnings, over a century of innovation has enabled mass scale, continuous motion, unbelievably low manufacturing cost. And when we think about the lithium-ion industry, which is really only in its 3rd decade of high-volume production, it has so far to go to achieve similar scale and simplicity. And that was the inspiration that we set out to the team as we thought about how to marry cell design and manufacturing in the best possible factory. And let's talk a little bit about what's in a cell factory. First, there's an electrode process where the active materials are coated into films onto foils. Then those coated foils are wound in the winding process we just talked about, where if you do have tabs, you have to start and stop a lot. Then the jelly roll is assembled into the can, sealed, filled with electrolyte, and then sent to formation, where the cell is charged for the first time, and where the sort of the electrochemistry is set and the quality of the cell is verified. And we set out at every step of this process to try to take that inspiration we just showed and think about how we make those processes fundamentally better and more scalable. And one of the most important processes is where it all begins, the wet process of the electrode coating. And just to give you all a sense of scale, I'm going to walk through what's in that wet process. You've got mixing, where the powders are mixed with either a water or a solvents for the cathode. That mix then goes into a large coat and dry oven, where the slurry is coated onto the foil, huge ovens, tens of meters long. dried, and that solvent then has to be recovered. You can see the solvent recovery system. And then finally, the coated foil is compressed to the final density. And when you're looking at this, you're like, wow, that's a lot of equipment for one step, especially when you consider that little speck next to the coating oven is a person. This is serious iron involved in making batteries. Wouldn't it be great if we could skip that solvent step, which is one of those dig a ditch and then fill it kind of things where you put the solvent in and then take it out and recycle it, and just go straight to dry mix to coat? And that's what the dry process really is about. And in the most basic form, you can see it here on a bench top. Literally, powder into film. As simple as that.
I mean, it's hard, actually, just to be clear. So, you know, if this was easy, everyone would do it. So it's not like dry coating electrode is actually easy. It's actually very hard to do what appears to be a simple thing. And it's worth noting, like, you know, we did acquire Maxwell as like a little over a year ago, I guess. And you know, it's certainly a good company and everything, but the dry coating they had was like, it's like sort of, I would call proof of concept. Since the acquisition, we've actually revved the machine that does dry coating 4 times. So we're in revision 4 post-acquisition of the machine. And there's still a lot of work to do. So I would not say this is like completely in the bag. It's still a lot of work to do. And you know, as you go from like benchtop to lab to pilot to volume production, there are actually major issues that you encounter at every level. It's not like, you know, you make something work on your bench and bingo, now you can make a bazillion of it.
Absolutely.
It's insanely difficult to scale up.
Yeah, but if you do scale it up,
yeah,
what you saw before becomes this.
Yeah.
So you can see the motivation. A 10 times reduction in footprint, a 10 times reduction in energy, and a massive reduction in investment. But as Elon was saying, simple is hard.
Yeah. Yeah, I mean, to be clear, I would like not say that right now it's just totally working. It's close to working, but it's not, even now, at the pilot plant level, it is close to working. Well, it's fair to say it does work, but with not a high yield.
Yeah,
so
we're still ironing out the kinks, but we've made tens of thousands of cells, thousands of kilometers of electrode. I mean, we are on the 4th generation of the equipment, so we've learned a lot along the way.
Yeah.
I mean, it is super demanding because every atom has its place if you want to deliver the energy density and the cycle life and the supercharging.
Yeah.
But we're confident that we will get there, but it will be a lot of work along the way.
There's a clear path to success, but a ton of work between here and there.
Yep.
So, but this is a really profound improvement. Again, for people that know battery manufacturing, this is gigantic. We'll probably be on machine revision 6 or 7 by the time we do large-scale production. The rate at which the machines are being improved is extremely rapid. Like literally every 3 or 4 months is a new rev.
Yeah, and beyond the electrode, we continue to innovate on every other process step. So let's talk a little bit about assembly, which is next. The key to a high-performing assembly line is accomplishing processes while in motion, continuous motion, and thinking of the line as a highway, max velocity down the highway, no start and stop, no city driving.
Exactly, no stoplights and traffic lights or anything. You want the highway.
I want the highway.
Yeah.
And together with our internal design team that makes this equipment and designs this equipment, we coupled thinking about how to make the best cell with thinking about how to make the best equipment so that we could accomplish the fastest parts per minute rates on all of these tools. And through all of that development, we were able to get to the point where we can implement assembly lines, one line, 20 gigawatt hours, 7 times increase in output per line. And when you're thinking about scalability and pure effort, having one line be 7x the capability is just effort multiplying.
Yeah. So. Yeah, you can sort of think about like the sort of the fundamental physics of a factory or something. Like, I think it's actually quite a lot like the rocket equation, where you've got basically in the rocket equation you've got your exhaust velocity and then the log of the start to end masses. So it's basically saying, you know, how fast are things going and what percentage of the factory volume is doing useful work. And conveyance does not count as useful work. So
only the value-added steps.
yeah, if you break the factory down into cubic meter sections, and say, or smaller, it could be like 1 liter sections, and say, is a majority of this volume doing useful work? You would be astounded at how bad most factories are. They're like maybe 2 or 3%, including our factory in Fremont. So I think it is possible to get to at least 10 times that volumetric efficiency. So more like 30% ish, maybe more, and be 10x better, which means the factory can be 10 times smaller. And then the other thing is how fast are things going through the factory? It's like speed and density. The faster you go, like if a factory that's moving at say twice the speed of another factory is equivalent to two factories basically, and the company that will be successful is the company that with one factory can accomplish what other companies take 2 or 3 or 4 factories to do. So this is what we're trying to do here is say, okay, how do we with one factory achieve what maybe 5 or even 10 factories would normally be required to achieve?
And the vertical integration with the machine design teams at Groman and Highbar and others allows us to really accomplish that, because we don't have all these edge conditions between one piece of equipment and another. We can design the entire machine to be one machine and remove all of these unnecessary steps.
Yeah, I mean, basically Tesla is aiming to be the best at manufacturing of any company on Earth. This is the thing that's actually most important in the long run. I think, just from a company standpoint and from basically achieving sustainability as fast as possible. But I think also for long-term competitiveness, eventually every car company will have long-range electric cars. Eventually every company will have autonomy. I think, but not every company will be great at manufacturing. Tesla will be absolutely head and shoulders above anyone else in manufacturing. That is our goal.
Manufacturing is hard, and hard problems are fun to solve. Okay, now let's talk about formation. In a typical cell factory, formation represents 25% of the investment. And what is formation? It's charging and discharging cells and verifying the quality of the cell. Turns out we've charged and discharged billions and billions of cells in our vehicles, so we know a thing or two about that. The typical formation setup is you charge and discharge each cell individually. In our car, we charge thousands of cells at once. And we took our principle and our power electronics, leveraging Powerwall, vehicle battery management systems, and others, to dramatically improve the formation equipment cost effectiveness and density. 86% reduction in formation investment, 75% reduction in footprint.
So.
You want to take this one?
Sure. So essentially, what this translates to, based on what we know today, is about a 75% reduction in the investment per kilowatt hour or gigawatt hour. It's just basically 4 times better than the current state of the art to the best of our knowledge. And I think there's probably room to improve even beyond that.
Definitely.
Definitely, yeah. So we're able to, from a volume standpoint, actually get what, in a smaller form factor than Giga Nevada, we were able to get many times the cell output. So you can see, like, basically we can get a terawatt hour in less space than it took to make a gigawatt hour, 150 gigawatt hours. So this is pretty profound. It's like, I would actually not have thought this was possible several years ago, that we could actually get to terawatt hour scale in less space than what we currently envision for doing 150 gigawatt hours.
Yes, simpler accelerates terawatt hour scale, and that's what we need to do to accelerate our mission. And as Elon said, we're going to try to even improve on this as we push towards our goals, which are.
Yeah. So this is just for. This is just talking about Tesla internal cell production. As I tweeted out earlier, we will continue to use our cell suppliers, Panasonic and LG and CATL. And so this is 100 gigawatt hours supplemental to what we buy from suppliers. And yeah, essentially, this does like reduce our weighted average cost of a cell because, but it does allows us to make a lot more cars and a lot more stationary storage, and then long term, we're expecting to make on the order of 3,000 gigawatt hours or 3 terawatt hours per year. I think we can. I think we've got a good chance of achieving this actually before 2030, but I'm highly confident that we could do it by 2030.
When you look at the size of that factory on the previous page, it really shows how enabling all of these advancements are in achieving a 3 terawatt hour goal by 2030. And not only is all of that manufacturing innovation fantastic for enabling scale, it's also an additional 18% reduction in dollar per kilowatt hour at the battery pack level.
But wait, there's more.
But wait, there's more.
Yeah.
So we have a manufacturing system. We've got a cell design. What are the active materials we're going to put in that cell design? Let's talk about the anode first. Let's talk about silicon. Why is silicon awesome? It's awesome because it's the most abundant element in the Earth's crust after oxygen, which means it's everywhere. It's sand.
Yeah. Sand is silicon dioxide.
Yeah. And it happens to store 9 times more lithium than graphite, which is the typical anode material in lithium-ion batteries today. So why isn't everybody using it? The main reason is because the challenge with silicon is that it expands 4x when fully charged with lithium. And basically, all of that expansion stress on the particles start cracking, they start electrically isolating, you lose capacity, the energy retention of the battery starts to fade, and it also gums up with a passivation layer that has to keep reforming as the particles expand.
Yeah, basically, with silicon, the cookie crumbles and gets gooey. That's basically what happens.
Good analogy.
Yeah.
And current approaches to solve this, which exist, I mean, we have silicon in the cars that you're all in right now, involved highly engineered, expensive materials in the scheme of things. Now, they're still great, and they enable some of the benefits of silicon. They just don't enable all of it, and they're not scalable enough. And you can see some of the things that maybe you've heard of, SiO, silicon with carbon, or silicon nanowires. I mean, that's kind of the space right now. What we're proposing is a step change in capability and a step change in cost. And what that really is to just go to the raw metallurgical silicon itself. Don't engineer the base metal. Just start with that and design for it to expand in how you think of the particle in the electrode design and how you code it.
Yeah, and I'm not sure if you saw this. Basically, $1 per kilowatt hours.
Yeah.
Basically, if you use simple silicon, it's dramatically less than even the silicon that is currently used in the batteries that are made today. And you can use a lot more of it.
The anode would cost, with this silicon, and the anode costs $1.20 a kilowatt hour.
Yeah.
And how does it work? Start with raw metallurgical silicon, stabilize the surface with an elastic ion-conducting polymer coating that is applied through a very scalable approach. No like chemical vapor deposition, no highly engineered high capex solutions, and then integrated into the electrode through a robust network formed out of a highly elastic binder. And in the end, by leveraging this silicon to its potential, we can increase the range of our vehicles by an additional 20%, just this improvement.
Yeah, it gets cheaper and longer range.
Yeah, and when we take that anode cost reduction, we're looking at another 5% dollar per kilowatt hour reduction at the battery pack level. And there's more. Let's talk about cathodes. What is a battery cathode? Cathodes are like bookshelves where the metal, the nickel, the cobalt, the manganese, or aluminum is like the shelf, and the lithium is the book. And really, what sets apart these different metals is how many books of lithium they can fit on the shelves and how sturdy the shelves are. Cobalt is a...
Yeah, sorry, I was just going to say, it's tough to exactly figure out what the right analogy is to explain cathode and anode, but a bookshelf is probably a pretty good one, in the sense that you need a stable structure to contain the ions. So you want a structure that does not crumble or get gooey, or basically that holds its shape in both the cathode and the anode. As you're moving these ions back and forth, it needs to retain its structure. So if it doesn't retain its structure, then you lose cycle life and your battery capacity drops very quickly.
Absolutely. Yeah, I totally agree. And I think people are always talking about like, oh, what's the cathode going to be? Is it NCA or whatever? You know, the thing to consider is just fundamentally what the metals are capable of, and that's what we have on the chart here. $1 per kilowatt hour cathode of just the metal, using just LME, you know, London Metal Exchange prices, versus the energy density of just the cathode. And you can see nickel is the cheapest and the highest energy density, and that's why increasing nickel is a goal of ours and really everybody's in the battery industry. But one of the reasons why cobalt is even used at all is because it is a very stable bookshelf. And the challenge with going to pure nickel is stabilizing that bookshelf with only nickel. And that's what we've been working on with our high nickel cathode development, which has 0 cobalt in it. Leveraging novel coatings and dopants, we can get a 15% reduction in cathode $1 per kilowatt hour.
Yeah. It's a big deal.
But it's not just about nickel. You want to?
Yeah, sure. So in order to scale, we really need to make sure that we're not constrained by total nickel availability. I actually spoke with the CEOs of the biggest mining companies in the world and said, please make more nickel. It's very important. And so I think they are going to make more nickel. But there's also, I think we need to have a kind of a 3-tiered approach to batteries. So starting with iron, that's kind of like a medium range, and then nickel manganese as sort of a medium plus, intermediate, and then a high nickel for long range applications like Cybertruck and the semi. Something like a semi truck, it's extremely important to have high energy density in order to get long range. So just to give sort of iron a bit more time, like although if you look at the watt-hours per kilogram at the cathode level of iron, it looks like nickel's twice as good. But when you've fully considered at the pack level, everything else taken into account, nickel is about maybe 50 or 60% better than iron. So iron is a little better than it would seem when you look at it at the pack level fully considered. It's not as good as nickel. Nickel is like 50 to 60% better, but it's actually pretty good. And so, good for stationary storage and for medium range applications where energy density is not paramount. And then, like I said, for intermediate, it's kind of a nickel manganese. And it's relatively straightforward to do a cathode that's 2/3 nickel, 1/3 manganese, which would then allow us to make 50% more cell volume with the same amount of nickel.
And with very little energy trade-off. I mean,
yeah.
Just enough to have you still want to use 100% nickel for something like a semi-truck, but really not much of a sacrifice at all.
Yeah.
And, beyond the metals, because a lot of people spend time talking about the metals, actually the cathode process itself is a big target. 35% of the cathode $1 per kilowatt hour is just in transferring it into its final form. And so we see that as a big target, and we decided to take that on. Here's a view of the traditional cathode process. Effectively, if you start at the left and you have the metal from the mine, the first thing that happens is the metal from the mine is changed into an intermediate thing called a metal sulfate, because that's just happened to be what chemists wanted a long time ago. And then when you're making the cathode, you have to take this intermediate thing called metal sulfate, add chemicals, add a whole bunch of water, a whole bunch of stuff happens in the middle, and at the end, you get that little bit of cathode and a whole bunch of wastewater and byproducts.
Yeah, it's insanely complicated. If you look at the total, like if you're just like, it's a small world journey of I am a nickel atom. What happens to me? And it's crazy. Like you're going around the world 3 times. There's like the moral equivalent of like dig in the ditch, fill in the ditch, and dig in the ditch again. It's total madness, basically. And these things just grew up as they're just kind of like legacy things that it's like how it was done before. And then they connected the dots, but really didn't think of the whole thing from like a first principle standpoint, saying how do we get from the nickel ore in the ground to the finished nickel product for a battery. And so we've looked at the entire value chain and said, how can we make this as simple as possible?
And that's what we're proposing here with our process. As you can see, a whole lot less is going on here. We get rid of the intermediate, metal, water, final product cathode, recirculate the water, no wastewater at all. And when you summarize all of that, it's a 66% reduction in CapEx investment, a 76% reduction in process cost, and 0 wastewater. Much more scalable solution.
Yeah.
And then when you think about the fact that now we're actually just directly consuming the raw metal nickel powder, it dramatically simplifies the metal refining part of the whole process. So we can eliminate billions in battery-grade nickel intermediate production. It's not needed at all.
Yeah.
We can also use that same process we showed on the previous page to directly consume the metal powder coming out of recycled electric vehicle and grid storage batteries. So this process enables both simpler mining and simpler recycling. And now that we have this process, obviously we're going to go and start building our own cathode facility in North America and leveraging all of the North American resources that exist for nickel and lithium. And just doing that, just localizing our cathode supply chain and production, we can reduce miles traveled by all the materials that end up in the cathode by 80%, which is huge for cost.
Yeah, I mean, to be clear, cathode production would be part of the Tesla cell production plant. So it would just be, basically, raw materials coming from the mine, and from raw materials in the mine, out comes a battery.
And on that note, the way the lithium ends up in the cell is through the cathode, so then we should obviously on-site lithium conversion as well, which is what we will do using a new process that we're going to pioneer. That's a sulfate-free process again, skip the intermediate. 33% reduction in lithium cost, 100% electric facility co-located with the cathode plant.
Yeah. So it's important to note that there is a massive amount of lithium on Earth.
Yeah.
So lithium is not like oil. There's a massive amount of it pretty much everywhere. In fact, there's enough lithium in the United States to convert the entire United States fleet to electric. Like all the cars in the United States, there's like 300 million or something like that. Every vehicle in the United States can be converted to electric using only lithium that is available in the United States.
Discovered today.
What we already know exists.
People really haven't even been looking.
Yeah, people haven't been trying because it's just like widely available. So, but it is important to say, like, okay, what is the smartest way to take the ore and extract the lithium and do so in an environmentally friendly way? And we actually discovered again, looking at a sort of first principles physics standpoint, instead of just the way it's always been done, is we found that we can actually use table salt, sodium chloride, to basically extract the lithium from the ore. Nobody's done this before. To the best of my knowledge, nobody's done this. And it's a sort of, all the elements are reusable. It's a very sustainable way of obtaining lithium. And we actually got rights to a lithium clay deposit in Nevada.
Over 10,000 acres.
Over 10,000 acres. And then the nature of the mining is actually, I think, also very environmentally sensitive in that we sort of take a chunk of dirt out of the ground, or remove the lithium, and then put the chunk of dirt back where it was. So it will look pretty much the same as before, and it will not look like terrible. And yeah, it'll be nice. Nice.
Yeah.
So
simply mix clay with salt, put it in water, salt comes out with the lithium, done.
It's pretty crazy.
Yeah. So we're really excited about this, and there really is enough lithium in Nevada alone to electrify the entire U.S. fleet.
Yeah, that's true. Actually, just what's in Nevada. That's basically there's so much damn lithium on Earth. It's crazy. It's one of the most common elements on the planet.
And eventually, as we said at the beginning, when we get to this steady state 20 terawatt hours per year of production, we will transfer the entire non-renewable fleet of both power plants, home heating and battery and industry heating, and vehicles to electric. And at that point, we have an awesome resource in those batteries to recycle to make new batteries. So we don't need to do any more mining at that point. And you can see why.
Yeah.
The difference in the value of the material coming back from the vehicle versus the ground, you'd always go to the vehicle. And we recycle 100% of our vehicle batteries today. And actually, we are starting our pilot full-scale recycling production at Gigafactory Reno next quarter to continue to develop this process as our recycling returns grow.
Yeah, I mean, to date it's been done by third parties, but we think we can recycle the batteries more effectively, especially since you know we know our batteries, we're making the same battery as the thing we're recycling. So whereas like third-party recyclers have to consider batteries of all kinds.
Yeah, and just to think about what this actually means, the recycling resource is always 10 or greater years delayed because batteries last a really long time. But eventually, it is the way that all resources will be made available, and that's why we're investing in this recycling facility in Nevada.
Yeah. Long-term, new batteries will come from old batteries once the fleet reaches steady state.
Right. Okay, so we just talked about scaling cathode and recycling. All of the benefits that you just saw are added to this benefit of a 12% reduction in dollars per kilowatt hour at the battery pack level. Almost at our halve the cost goal, but there's one more section. Take it away, Elon.
So there's an architecture that we've been wanting to do at Tesla for a long time, and we finally figured it out. And I think it's the way that all electric cars in the future will ultimately be made. It's the right way to do things. So it starts with having a single piece casting, or a single piece casting for the front body and the rear body. And in order to do this, we commissioned the largest casting machine that has ever been made, and it's currently working just over the road at our Fremont plant. We have it's pretty sweet. Currently making the entire rear section of the car as a single piece, high pressure die cast aluminum. And in order to do this, we actually had to develop our own alloy because we wanted a high strength casting alloy that did not require coatings or heat treatment. This is a big deal for castings, especially with a large casting. If you heat treat it afterwards, it tends to deform. It kind of like does this like potato chip thing. So it's very hard to keep a large casting to have its shape. So in order to achieve this, there was no alloy that existed that could do this. So we developed our own alloy, a special alloy of aluminum that has high strength without heat treat and is very castable. So that's a great achievement of our materials team. In fact, in general, we've got a lot of advanced materials coming for Tesla, new alloys and materials that have never existed before. So you're basically making the front and rear of the car as a single piece, and then that then interfaces to what we call the structural battery, where the battery for the first time will have dual use. The battery will both have the use as an energy device and as structure. This is absolutely the way things are done. In the early days of aircraft, they would carry the fuel tanks as cargo. So the fuel tanks actually were quite difficult to carry. They were like basically worse than cargo. You had to kind of bolt them down. It was very difficult. And then somebody said, "Hey, what if we just make the wing tanks? What if we just make the fuel tank in wing shape?" So all modern airplanes, the fuel tank, your wing is just a fuel tank in wing shape. This is absolutely the way to do it. And then the fuel tank serves as dual structure, and it's no longer cargo. It's fundamental to the structure of the aircraft. This was a major breakthrough. We're doing the same for cars. So this is really quite profound. Effectively, the non-cell portion of the battery has negative mass. So we save so much mass in the rest of the vehicle. We save more mass in the rest of the vehicle than the non-cell portion of the battery. So it's like, well, how do you really minimize the mass of a battery? Make it negative. Make the battery non-cell portion of the battery pack negative. It also allows us to pack the cells more densely because we do not have intermediate structure in the battery pack. So instead of having these like supports and stabilizers and stringers and structural elements in the battery, we now have a lot more space in the battery because the pack itself is structural. What we do is essentially instead of having just a filler that is a flame retardant, which is currently what is in the 3NY battery packs, we have a filler that is a structural adhesive, as well as flame retardant. So it effectively glues the cells to the top and bottom sheet. And this allows you to do shear transfer between the upper and lower sheet. Just like if you have like a Formula One craft or like a racing boat, and you have carbon fiber face sheets and say aluminum honeycomb between them, this gives you incredible stiffness. And it's really the way that any super fast thing works is you create basically a honeycomb sandwich with two face sheets. This is actually even better than what aircraft do, because aircraft do not do this. They can't do this because fuel is liquid. So in our case, the batteries are solid. So we can actually use the steel shell case of the battery to transfer shear from the upper and lower face sheet, which makes for an incredibly stiff structure, even stiffer than a regular car.
Yeah.
In fact, if this was like a convertible that had no upper structure, it would be stiffer than that convertible would be stiffer than a regular car. So this is it's just really really major. So it improves the mass efficiency of the battery, and then those castings are also quite important because you want to transfer load into the structural battery pack in a very smooth, continuous way, so you don't put arbitrary point loads into the battery. So you kind of have to, you want to sort of feather the load out from the front and rear into the structural battery. It also allows us to to move the cells closer to the center of the car, because we don't have the in the top one we've got that sort of all the supports and stuff. So the volumetric efficiency of the structural pack is much better than a non-structural pack, and we actually bring the cells closer to the center, and because they're closer to the center, it reduces the probability of a side impact potentially contacting the cells, because it has to go, any kind of side impact has to go further in order to reach the cells. It also improves what's called the polar moment of inertia, which is that you can think of like when there's a ice skater, arms out or arms in. Arms in, you rotate faster. So if you can bring things closer to the center, you reduce the polar moment of inertia, and that means the car maneuvers better. It just feels better. You won't know why, but it just feels more agile. So it's really cool. This is really major. Like I said, so 10% mass reduction in the body of the car, 14% range increase, 370 fewer parts. So, I mean, I really think that long term, in any cars that do not take this architecture will not be competitive.
And it's not just at the product level a better product, but in the factory, it's a massive simplification. You saw the part removal. It's casting machines. It's the structural battery pack. So we're looking at over 50% reduction in investment per gigawatt hour, 35% reduction in floor space, and we'll continue to improve that as we make the vehicle factory of the future.
Yeah, so major improvements on all fronts, from the cell all the way to the vehicle.
And in addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah. Yeah.
All right, so stacking it up. We're not just talking about cost or range. We've got to look at all the facets. So range increase, we're unlocking up to 54% increase in range for our vehicles and energy density for our energy products. 56% reduction in dollars per kilowatt hour at the battery pack level, and a 69% reduction in investment per gigawatt hour, which is the true enabler when we talk back about how do we achieve this scale problem here.
Yeah. And yeah, so I think it's pretty nice that investment per gigawatt hour reduction is 69%. I mean, who would have thought?
Yeah, just happened to happen out that way. Okay.
I mean, 0.420%, of course. Yeah, so what this enables us to do is achieve a new trajectory in the reduction of cell cost. And now, to be clear, it will take us probably a year to 18 months to start realizing these advantages, and probably to fully realize the advantages, probably it's about 3 years or thereabouts. So, it's not like if we could do this instantly, we would. But it's really, I think what this bodes for, it just really bodes well for the future, and means that the long-term scaling of Tesla and the sustainable energy products that we make will be massively increased. So, what tends to happen as companies get bigger is things tend to slow down. Actually, they're going to speed up.
And they have to speed up if we're going to accelerate the transition to sustainable energy.
Yeah. I mean, long term, we want to try to replace about, at least 1% of the total vehicle fleet on Earth, which is about 2 billion vehicles. So long term, we want to try to make about 20 million vehicles a year.
But I think it's important to point out that when we talked about 3 terawatt hours by 2030, the problem is a 20 terawatt hour problem. So everybody needs to be accelerating their efforts to accomplish these objectives. Doesn't matter where you are in the value chain, there is a ton to do. You need to rethink from first principles how you do it so that you can scale to meet all of our objectives.
Yep.
And Elon?
Sure.
What does this mean?
What does it mean? What does this mean for our future products? We're confident that long term we can design and manufacture a compelling $25,000 electric vehicle. This has always been our dream from the beginning of the company. I even wrote a blog piece about it because our first car was an expensive sports car, and then it was like slightly less expensive sedan, and then finally sort of a, I don't know, mass market premium, but like the Model 3 and Model Y. But it was always our goal to try to make an affordable electric car, and I think probably, like I said, about 3 years from now, we're confident we can make a very compelling $25,000 electric vehicle that's also fully autonomous.
And when you think about the $25,000 price point, you have to consider how much less expensive it is to own an electric vehicle.
Yeah.
So actually, it becomes even more affordable at that $25,000 price point.
Yeah. So we have and extreme performance and range, and we should probably talk about the Model S Plaid. What about that? Yeah. Woo. So, we took the latest Plaid out to Laguna Seca on Sunday. It got a minute 30, and we think probably there's another 3 seconds or more to take off that time. So we're confident the Model S Plaid will achieve the best track time of any production vehicle ever, of any kind, two-door or otherwise. And you can order it now, and it's available basically end of next year. So, and now we'll move to Q&A.
Absolutely.
So we'll invite a few people on stage.
Come on up, team.
So this is just a small portion of the team, but it would be great to show you some more of the team, and when we do Q&A, we can give various people different questions to answer.
Sounds great. Actually, I don't know how we're getting the questions.
Actually, I don't know either. Okay, well, you could just you can maybe get out of the car for 2 seconds and yell it at us. I don't know. Hey, how do we get any questions?
Oh, they're mics. Okay, wait for the mic.
Oh, there are mics. Okay, great.
All right.
Okay, we'll definitely need to give people mics because otherwise there's no way. Sorry? All right, we're going to pass some mics out. We don't have a name for the $25,000 car yet.
It's a great question, though.
Yes, we will be manufacturing cells in Berlin. Yep.
Thermal management system? For homes.
Oh, you mean like the home HVAC? Yeah, that's a pet project that I'd love to get going on. I don't know, maybe we'll start working on that next year. Because I just think you could really make a way better home HVAC system that's really quiet and super efficient and super energy efficient, and also has like a way better filter for particles, and and it works very reliably. And we've already developed that for the car. Like, so the heat pump in the Model Y is really pretty spectacular. I mean, it's tiny, it's efficient, it has to last for 15 years. It's got to work in all kinds of conditions, from the coldest winter to the hottest summer. So we've actually already done a massive amount of the work necessary for a really kick-ass home HVAC. And they could also like stack them. So if you want to say, depending upon the size of your house or whatever, how much you need, you can just basically stack them, and just have a very compelling, super efficient home HVAC. And then you can also communicate with the car, and it'll know when you're coming home. So it's like, oh, I don't need to keep the house cold all day. I just cool it down because I knew you were coming home. So the pack can communicate with the car and just like really dial it into when you actually need cooling and heating. It'll be great.
Fun product.
Yeah.
Who's next?
Hello. Hey guys, Eli here from Tesla Owners Club, My Tesla Adventure. Just quick question. So I'm a huge fan of car camping in my Tesla with my dream case, like my all-time favorite activity. Is it going to be possible to get climate control to the back of the Cybertruck? Because that would be the ultimate camping machine if we can get all-night climate control.
We'll try to do that. Thank you. I agree. That would be really cool. Yeah.
All right, who's next?
Hello. Long-time fan, Elon. Great guy. Just a question. How does the ICE industry look like in the future?
Well, I don't think there will be an ICE industry long term. Yeah. I mean, well, I guess there might be like a few things that are like, it's a like curious thing. Like, I mean, there's still like some steam engines made somewhere, but like they're just basically sort of quirky collector's items. I mean, that will be the future of the internal combustion engine car.
Hi, Elon, to your left here in the white Model Y. Ryan McCaffrey from the Ride the Lightning Tesla podcast. Curious about Cybertruck. It was interesting to see where you had it in on the battery technology front. I'm sort of curious what you see for it in the production front. Is its volume, trucks are so popular in America, do you see its volume equaling the 3 or the Y in the future? And also, were you able to get Tesla is able to legally be sold in Texas as part of the Giga Texas deal?
Well, it's hard to say what the volume exactly would be for the Cybertruck. The orders are gigantic. So we have like, I don't know, well over 500,000 orders. I think maybe 600,000 or 600,000. That's a lot, basically. We stopped counting. So I think there's probably room for, I don't know, at least like a unit volume of like 250 to 300,000 a year, maybe more. Now we are designing the Cybertruck to meet the American spec, because if you try to design a car to meet the global, the superset of all global requirements, it basically, you can't make the Cybertruck. It's impossible. It really is designed for the American market, but this is the biggest market. Our North American market is the biggest market for pickup trucks by far, or large pickup trucks. And then I think we'll probably make an international version of the Cybertruck that'll be kind of smaller, kind of like a tight Wolverine package. It'll still be cooler, but it'll be smaller, because you just can't make a giant truck like that for most markets. So yeah, but it's going to be great. And I don't know. I think probably we'll be able to sell directly in Texas. We do pretty well right now, but it is a bit weird not being able to actually conclude a transaction in Texas. But it's got to be like, you know, a click on a server based in California. So, but weirdly, we can do leasing in Texas, but not selling. But hopefully that'll get cleared up in the future.
Yeah, Elon, great job with everything that you're doing. Thras Gerber from Gerber Kawasaki, your team's amazing. What I'm most curious about, these innovations are incredible, but on my drive up here, fully on autopilot for 400 miles, the entire state is brown, and this is ultimately about climate. Has there been some analysis done if all these things are achieved? What will its direct impact be on climate?
Well, I mean, I think it will have a very significant impact because it will stop the CO2 ppm from growing as it is every year. And I mean, I should say, like, I try to view the whole climate thing as a science question as much as possible. Science, you always question your hypothesis. Is it true? Is it not true? Or assign a probability to a given hypothesis. And I should say that my original interest in electric vehicles predates the climate issue. Like just when I was in high school, I thought, man, if we don't figure out electric cars, the whole economy is going to collapse when we run out of oil. So it's like, we better figure out electric cars and sustainable energy, or civilization is going to crumble. And then it was only kind of later that the significance of the climate risk became apparent. We were also able, using fracking and other types of technology, to access a lot more fossil fuels than previously thought, which is, helpful for lowering the cost of gasoline, but it's pretty bad for the total tonnage of CO2 that you could put in the atmosphere. It's now greatly beyond what people previously thought. So, but this is, as we were just going through this presentation, it's like it is a absolutely monumental task to accelerate the advent of sustainable energy. I mean, the entire global economy is still, more than 99% dependent on, or roughly 99% dependent on fossil fuels. So although electric cars kind of get a lot of press right now, they're still, and there's still very few, as a percentage of the total global fleet, is practically nothing. I would say, yes, less than 1% of the global fleet is electric right now. Because of 2 billion cars and trucks and whatnot in use. So there's a massive amount of work ahead, just insane, like hard to comprehend how much work is ahead to get the new vehicle production to be sustainable, to massively increase the amount of stationary storage, which is critical because renewable energy is intermittent. Wind and solar is intermittent. Sometimes the wind doesn't blow, and obviously sun doesn't shine at night. So you got to have batteries, a massive number of batteries. So
it's hard to measure in direct impact, but it's an experiment that we shouldn't be performing. And the sooner we can sort of end the experiment, the sooner we can kind of move on in a fully sustainable way that is actually lower cost. I mean, I think the thing that people haven't fully internalized is once we do get to the 25K car, the ownership cost of that car is incredibly lower than the prior car. And then on the solar side and wind, with the cost of solar and wind coming down and with batteries coming down with them, the actual cost of energy on the grid is going down. So we're sort of moving towards a sustainable, lower cost future. So there's not really a sacrifice.
Yeah, that's true. It is a false dichotomy to say that it's either prosperity or sustainability. This is often used, by oil and gas to say like, oh, well, do you want people to lose their jobs? Do you want lower people's standards of living? Do you want to, make all these economic sacrifices, really, in order to have sustainability? And the reality, as Drew was saying, is that a sustainable energy is going to be lower cost, not higher cost, than fossil fuels.
Elon, quick question for you, right here in front. First, thanks for having everyone, and as telling a friend, the one company to go work for that's going to have the biggest structural impact over the next 10 years at scale, it's probably Tesla. So kudos to everyone at Tesla for what they've done to this point and going forward. The two questions for you, as you've looked at the auto and the storage markets, I know you've talked about it kind of 50-50 long term, but it seems like a lot of the battery cost curve achievements that that you've presented today really make some of these storage opportunities much more feasible over the next 5 years. And so I guess the first part of the question is, does your calculus upon learning and improving these things change on that 50-50 mix, or is there a role where storage becomes bigger? And then the second part of the question, with all these huge grand visions, who's going to be with Tesla from a corporate perspective accomplishing these things? Obviously, Tesla can't do it alone, but when you look at some of the traditional auto industry or power, et cetera, I don't see a lot of other Teslas.
Well, actually, so there's a lot of companies in China that I think are doing great work with electric vehicles and also with stationary storage. Although we don't see that much in the US yet, but I think probably we will in the future. I don't know. I mean, obviously, we're doing everything we can to encourage other companies to move to sustainable transport and also, make stationary storage batteries. We opened up, made our patents freely available. We really try to tell these companies, hey, you really need to do this or you won't exist in the future. But they don't believe it, So, I mean, we've talked until we're blue in the face. What are we supposed to do? But we really are hopeful that other companies will also do what we're doing, and that will make a sustainable future come sooner.
From a fundamental market size perspective, like we did the first ground up work to show the size of the market in terawatt hours, and they are roughly 50-50. 10 terawatt hours for transportation, 10 terawatt hours for the grid. And part of that is because the grid batteries, because when you're making a power plant, you're making a large investment, our 25-year assets are greater. If the grid batteries were 10-year kind of things, the grid market would be bigger. But because it's a longer duration asset, they're roughly the same size.
Thinking long term, is there any other segments that this new battery will be able to disrupt or electrify beyond just the initial Model 2 or cheaper sedan, like a boat, boring company loop, plane, boat?
Where are you, Gali?
Are you there? What's up? Right here.
Okay, great.
It's like
ventriloquism here, It's like we just get the sound out of the speaker and you can't tell where the heck it's coming from.
Yeah, any hints, or is the Model 2 such a big deal because it decreases the cost of transportation that is really the disruption? Or should we get hyped that this new cost curve opens up different vehicle categories like a high passenger density bus, boring loop, boat, plane?
I mean, there are batteries in limited production right now that do exceed 400 watt-hours per kilogram, which I think is about the number you need for decent range, medium range aircraft. I think our batteries will, over time, start to approach the 400 watt-hours per kilogram range as well. Yeah, I mean, I think over time we'll see all modes of transport, with the ironic exception of rockets, transition to sustainability, or to electric, basically. On the rocket front, what we're planning to do is about 80% of Starship is liquid oxygen, and we're actually already running a power line to be able to use wind power to create the liquid oxygen. So we're making some decent progress on sustainability on the rocket front, but there's just no way to have an electric rocket, and it's important for the future of life and consciousness that we become a multi-planet species. So got to keep doing that.
Hi, Elon.
Hello.
Josh Phillips here, retail investor. I have a question in regards to the lithium and nickel industries and the likely price spikes and shortages of high-grade materials the EV industry is likely to see if they don't act fast to address future supply. Tesla have clearly made the right moves that are necessary, but there's a real worry that the potential supply issues and price spikes will create a drag on the rest of the EV industry and therefore a drag on global EV adoption. What advice would you give to the EV and mining industries to quickly solve this looming hurdles? Because for a sustainable energy future, the spice must flow. Thank you.
Yeah, indeed. The spice must flow. The new spice. I don't know. I think I'm not sure. I guess we can try to like basically overdo it in cell production and perhaps supply cells to others. But we do see the fundamental constraint as total cell production. That's why we're putting so much effort into making cells and kind of trying to reinvent every aspect of cell production from mining the ore to a complete battery pack. Because it's the fundamental constraint. We're not getting into the cell business because we, just for the hell of it. It's because it's the fundamental constraint. It's the thing that is the limiting factor for rapid growth. But we could certainly try to overdo it on cell production and perhaps sell cells to others. Although we are going at absolute top speed, so it's not like we're holding it back. But I think just making really efficient cars and that have low drag coefficient, low rolling resistance, efficient powertrains. I mean that's kind of what we've done in order to make iron phosphate still have a good range. So the iron phosphate's lower energy density solution, but there's while there are some limitations on the total amount of nickel produced every year, there's really no limit on the iron. There's so much iron, it's ridiculous. So you can really scale up iron phosphate, at a raw materials basis faster, more than you can nickel. But yeah.
And just to point out, when we were walking through this presentation, we intentionally separated all the different aspects. The benefits of structural battery apply to a iron-based cathode in the same way they apply to a nickel-based cathode.
Yeah.
So you get longer range iron-based vehicles, and also the silicon benefit can apply to the iron-based vehicles as well. So we can do a lot to extend the range of an iron-based vehicle, which is why it's a key part of the roadmap going forward. And then I invited Turner up here to talk about what the mining industry can do.
Yeah. Diversification on the cathode side is obviously massive, and EVs are all about efficiency. And so for the EV industry, for the vehicle industry, we need to see powertrain efficiency really increase at all other companies matching Tesla powertrain efficiency so that everyone can have that diversified cathode approach where LFP is used in medium range and even really make a 300-mile vehicle with LFP. And really the goal that we were trying to present here was a model for vertical integration, strategic vertical integration that a lot of different people can do. What we need to see is vertical integration that shortens the process path from mine to cathode. And what we're doing here is novel, and we're trying to push the industry in that direction. So we're presenting a model here that anyone can follow.
Yeah, in fact, if there's anything that you guys want to comment on, feel free to step forward and say something.
I think the key is to be smart about your chemistry choices, your materials choices.
Spoke louder.
Yeah, if you're smart about your materials choices, the spice will continue to flow.
Yeah.
You don't need to use the same kind everywhere, and it's about strategically planning it out. And for miners, I think we are incentivizing them quite a bit to ramp up their production.
Yeah, and actually we had good calls. Like they're all motivated. I think that they've been sort of sitting back being like, are you going to grow like crazy? And we're like, yeah, we're going to grow like crazy. And then I think this indicates we're going to grow like crazy, and that's what the miners want to hear, and then they'll go make the investments.
Hello, Elon. This is Ben Limpick. I'm a musician. I was wondering, does Tesla have any future plans to make partnerships with music companies like it has done with Tencent Games or things like that for you guys to actually kind of expand your services for artists and other types of creative people to get involved in producing content that can be part of the Tesla ecosystem, or so other people that do creative things can get involved with you guys?
Well, we don't. We haven't really thought about that much, but I suppose it's probably something we should think about. We will be providing a title on Teslas. So we're providing more music sources that people can choose from, and generally trying to improve the entertainment experience in the cars. And I think actually as we go to a more autonomous future, the importance of entertainment and productivity will become greater and greater. I mean, to the degree that if you're just basically sitting in your car, the car is fully autonomous and driving somewhere. It's sort of like being in a, you know, the car is essentially your chauffeur, and then the things that become important are, okay, well, let's have good entertainment, and you know, if you want to do some productivity stuff, then that actually starts to become much more important because you're no longer spending your attention driving the car. So it will be extremely important in the future.
Should we do some of the say.com questions? Yeah. Okay. Should we do the second one?
Yeah, the first one I think we already answered. Like, if we're able to make enough cells, which we'll try to do, or we will supply other companies. It's definitely not an intentional effort to keep the cells to ourselves. If we can make enough for other companies, we will supply them. And we're trying to do, you know, the right thing for advancing the sustainable energy, whatever that is. So, vehicle to grid, we get asked that a lot. I think one of the things that's important to note is the vehicle to grid. It doesn't, unless you have a power cutoff. Like, you need to cut off your main supply to the grid. Otherwise, if you lose power in your house, you'll basically just backflow energy to the grid. So just having a reversal in the power flow does not actually keep the lights on. You need a whole separate system to cut off power to the grid. And I think there's also the case that people really want the freedom to be able to drive and to charge at their house. And it's obviously really problematic if you know, you get to morning and your car, instead of being charged, it discharged into the house, and then you're sort of, okay, now I can either drive or use the battery to power my house. I think it's actually going to be better for people's freedom of action to have a power wall and a car separate, and then it's you know, everything works. You know, and you add that, you basically combine that with solar, either solar retrofit or solar glass roof, and local battery storage. So you basically become your own utility, and then the car is you know, can be charged also with solar. I think that's like the stuff that works. You know, that said, like, we can certainly do vehicle to grid. And I think we could basically enable that with software in Europe or something, right?
Yeah. We are future generations of power electronics. We will be able to do this more or less everywhere from a like energy market participation perspective. But yeah, from a backing up the house, and it just so happens that the way the North American connectors are on all the cars in North America, it doesn't matter whether it's the Tesla connector or the connector that the other vehicles have, doesn't actually support powering your home. It's unfortunate. So you'd need an additional hardware to do that. But yeah, in the future, all versions of our vehicles will be able to at least do bidirectional power flow for the purposes of energy market participation. But even for that, it's important to remember that your car isn't plugged in 24/7. So it's kind of an unpredictable resource for the grid. It'll have a value, but it's not the same as a stationary battery pack.
Yeah, honestly, a vehicle to grid sounds good, but I think actually has a much lower utility than people think. I think very few people would actually use vehicle to grid, and we actually had with the original Roadster, we had vehicle to grid capabilities. Nobody used it.
Yep. How do we find the engineers to do everything we're saying?
How do we find the engineers to do all these things? Well, I guess we recruit a lot of engineers from all parts of the world. You know, I think Tesla has a good reputation for doing exciting engineering, and that tends to attract a lot of the top engineers in the world, because they know that their efforts at Tesla will really serve the greater good, and we're super hardcore about engineering. You know, Tesla is like first and foremost an engineering company. It's like hardcore engineering is what we do. Like the sheer amount of hardcore engineering done at Tesla is insane. And if you look at, say, there's various surveys done of engineering schools, where do you want to go? Like, what's your top choices? And actually, the top two choices last last few years have been Tesla and SpaceX. So sometimes it's Tesla first, sometimes SpaceX first, but those are the two top ones.
Yeah, I mean, if you are motivated to solve some of these problems, which are the hardest problems in the world to solve, that really fundamentally enable the future we all need, please reach out.
Yeah, and
help us work on these problems.
Absolutely, and like you said, the battle is far from over. Less than 1% of the global automotive fleet has been converted to electric, and even maybe less than 0.1% of stationary storage has been done. So stationary storage has barely begun. Converting the global vehicle fleet to electric has barely begun. So there's still a massive amount of engineering work to be done at Tesla and other companies to accelerate this transition to sustainability.
Hey, can you guys hear me?
Yeah.
This is Jordan from Mark Asset Management. So you've talked about the importance of the factory, and you've mentioned the ground-up design process and a lot of the new things that you're going to be doing or started to do in Shanghai, Berlin, and Austin. Can you just maybe help us understand and quantify like how financially meaningful all of those improvements will be? And then given what you're trying to accomplish as a company, is it fair to assume that the vast majority of improvement will be given back to the customer in the form of lower prices?
Yeah, I mean, I think certainly we will try to give back as much as possible to the customers. It's not like, it's not like Tesla's profitability is crazy high. Our average profitability for the last 4 quarters is like maybe 1%. So just to be clear, it's not like, we're minting money. Our valuation makes it seem like we are, but we're not. We do want to try to make the price as competitive as we can without like losing money. And if you lose money, then if you keep losing money, you'll just die. So we have to. This thing called profit is just like we need to bring in more money than we spend, otherwise we're dead.
But affordability is key to how we scale,
Yeah.
right? Like the demand goes nonlinear as you reduce the price of the car.
Yeah, I mean, it's important to sort of separate the difference between affordability and value for money, or desirability of the product. So, for a lot of people, they want to buy a Tesla, they simply don't have enough money. We could make the car infinitely desirable, but if somebody does not have enough money, they can't buy it. Sometimes, people, kind of forget this. It's like, it's like people have to have enough money to buy the car, and just making a car super desirable but expensive does not mean they can afford it. So it's absolutely critical that we make cars that people can actually afford. Yeah. So we should
over
go
here
some of these things. Just scroll down or something. Oh.
When do you expect Tesla vehicles to beat ICE vehicles on initial purchase price? I think a way to answer that question is, in the classes of vehicles we sell today, we're already doing that.
Yeah, we're already pretty close. And then factoring in total cost of ownership, and the fact that electric vehicles require much less servicing, and are way cheaper to run. When you look at like total cost of ownership, and you can obviously lease a car. So if you just like lease a car or get a loan for a car, you've got your sort of monthly payment, and then your cost for either gasoline or electricity, and your cost of servicing. And the fully considered cost of an electric car is much less than a gasoline car of the same nominal purchase price. I mean, that said, and like maybe on the order of 3 years, when we can do a lower cost car, like a $25,000 car, I think that will be basically on par, maybe slightly better than a comparable gasoline car. So I think maybe it's on the order of 3 years-ish.
How have the technology advancements and increased vertical integration of battery manufacturing influenced your ability to improve the environmental and social impact of the supply chain? And I think, yeah.
I think we sort of have said that already.
Yeah.
Do you have some ability to scroll through this? Just scroll away.
We covered recycling.
Yeah. Well, just scroll until we've got stuff that we haven't covered.
Well, we definitely covered that top
yeah,
one.
a lot of the things we've already answered, I think.
Covered that. That one.
I think we literally just answered that.
Yeah. Oh, I saw a cathode durability question. Let's go to that one. Go down, go down, go down. Good technical question. Keep going. How are you going to address the cathode durability and cost and environmental impact trifecta? Is this something you're going to leave the upstream supply chain to solve? No, I think we tried to answer that directly. I mean, we really are looking at not just what happens in the cathode facility, but like currently outside the cathode facility that should really be inside, and removing processes that shouldn't have been there in the first place, and the use of reagents that are just costly and not necessary, and removing a bunch of wastewater from the process.
Guys, is there anything you want to add to? Maybe we could like go through everyone and like maybe say what you're doing and say a few words. I don't know.
Sure. I just want to reiterate the fact that this is a massive problem.
Massive problem.
And it seems like Tesla's on its way and ahead, but we need everybody's help because it's everybody's planet, and we're not going to get to 20 terawatt-hours by ourselves. So please think about this carefully as it affects everybody. So let's get on it.
And obviously, if you care about solving sustainability and doing hardcore engineering, definitely come work at Tesla.
Yeah, we went through a couple of the manufacturing improvements, and it kind of looks easy when you put together a nice slide deck, but the challenges are like this. It's super challenging when you take materials out of the process, when you integrate processes together. You have to do a lot of things at once, and that's like this immense engineering challenge. And so, like, to appreciate that, like, you need, like, to get through this, we need, like, the best engineers we've got. And we've got this awesome team. I just want to shout out also to all of our team watching. Like, you guys are awesome. Like, you absolutely kicked ass putting this together. And, yeah.
Yes. Thank you.
Thank you, Tesla team. Totally agree.
Yeah, that's it. Like, yeah.
Okay. Yeah. Rodney Westmoreland, managing the construction here at Tesla. What I would like to say is, one, shout out to the team. The team has been working effortlessly. A very, very tough project here for 24 hours a day, it seems like, around the clock to have this complete. The thing that sets us apart from a lot of other construction, we have a construction company here. The thing that sets us apart is that we're integrated in the manufacturing process. So every detail that comes from Drew's mouth is directly implicated into the system that we're building. That way, what would typically take 3 or 4 months to create a specification, our design team is working right with the manufacturing team to allow us to speed that process up tremendously. So.
Yeah, it's definitely a important part of the vertically integrated approach is to be able to design the factory around the equipment, in fact, together with the equipment, so that you can build the factory at lower cost and more quickly.
Yeah, I'm Scott. I focus on cell design. I think it's hard to put into words how inspiring this is. I've been at it for a long time with Tesla, and
yeah,
I really hope others do join us.
Since when, Scott?
Since 2005. Yep,
yes,
with many of you. But thank you. It. 6. Yeah, a year before Drew, but who's keeping track? But I'm really stoked at what the team's been able to accomplish over the last, short period of time, about a year. It's been really an incredible transformation. I mean, hopefully what we've shown you inspires you to join us or join somebody else in the effort. And I couldn't think of a greater, more intelligent, more hardworking team to be working on with this problem.
Hi, Peter. I lead the manufacturing improvement team. And I guess the point that I would like to make is manufacturing improvements is like the accelerator. So like you think about the execution that Rodney talked about in terms of how fast we've been able to put together this factory, which is amazing and something that's been really incredible to be a part of. That's not enough. What we need to do is improve the manufacturing technology. That's the real accelerator. And that's what we're really focused on. Elon talks about it all the time, that really going and improving that system is what will enable us to get to the scale and the cost that we need. And then the other point that I would make is on the recruiting side, like, it doesn't matter if you know about batteries. If you come from any industry, you can do something fantastic in the work that we're doing. We talk to people from industries that you wouldn't imagine. Like, I talked to a guy who makes golf balls, and he has stuff which is really impactful for what we're doing. So, you know, if you're in any industry and you want to be, you know, impactful here, like, come join us. It'd be great.
Hi, excuse me. Hi, I'm Tony. I've been working in lithium and cathode materials for almost 23 years now, and this is the most growth I've seen in a company. I've been here a little over a year and a half. We're hiring amazing people that are allowing us to leverage technology that most of the industry is struggling to achieve. So to answer the question, how are we going to do this? We are really advancing the materials manufacturing for cathodes and for lithium beyond what has been accomplished in the previous 20 years.
It's exciting.
Yeah, my name's Turner. Work closely with the team. I've worked a lot with everyone here, and on the cathode and upstream materials side, it's really important that everyone understand that this growth is coming. This growth is real. We are going to make all of these batteries, and everyone needs to grow with us. The entire supply chain needs to grow with us. And if you have an idea that simplifies anything in the supply chain, come talk to us, come work with us, and let's do it.
Any existing specification is wrong. Any existing manufacturing method is wrong. Process equipment, it's wrong. It's just a question of how wrong.
Yes.
Quote
Exactly.
Elon Musk.
Yes, exactly. We're wrong. Just a question of how wrong. Just try to be less wrong.
So tell us how we're wrong and how we could do it better so that we can accelerate and improve as fast as possible.
All right. Well, I guess thank you everyone for coming. I hope you liked the presentation. Very exciting future ahead. You know, we're going to work our damnedest to transition the world to sustainable energy as quickly as possible, and your support and help is key to that success. So thanks again, super appreciated, and look forward to the next event. Thank you.
Thank you.
So, welcome to this beautiful live stream here on this channel. Let me just switch on the light. Here we go. This is how we like it up and light it up here on this channel. So, yeah, let me know in the comments where you are watching from, but the numbers of Tesla are gigantic, okay? I don't know where are now... where they are sitting. I think, let me have a look. Tesla, TSLA. All right, so Tesla is a little bit down as of this moment, but that is because the expectation were very, very big. So it was very hard to prove here somebody that Tesla will do great. But in the end of the day, it's not about that at Tesla. Tesla is about just this continuous growth, right? Because Wall Street was hammering the stock, and we were right in the end of the day to say, okay, Tesla is the nice stock that is currently out there, that is very, very much undervalued, that now everybody knows that Tesla is doing great, okay? Anyway, let's have a look. So Q3 update is as follows. It started as usual with the highlights, and here it started already fantastically, okay? So a free cash flow of $1.3 billion compared to about 600 million in the first or in the quarter before. Then you have here an operating income of $2 billion, 1.6 gap net income. So record numbers indeed. Here a little bit of a little bit of summary. I guess they will talk about the margin, because the margin obviously helps in this quarter because they sold the SNX, which is very high margin, right? They will talk about here a little bit about Germany and what is the status about that. The margin is fantastic, guys. 28.8% X credit. That's a new record, guys. And yeah, so here you can see the quarter over quarter and year over year, 74%. Okay. This kind of numbers are ridiculous at some point, and it's great that such a big company can still deliver this kind of growth. Okay, so that's quite interesting. And here you can see then that the operate expense went a little bit higher, yes, of course, but also the income from operation went much higher than obviously. And then here you have the crazy net income that went year over year 390%. That's really fantastic, guys. Okay, it's just this unbelievable growth. And here you can see in the first sentence total growth, revenue growth of 57% year over year, guys. Okay, you have here the total revenues were now $13 billion, guys. And I remember when Tesla just made about 20 billion for the whole year. Okay, so that was quite interesting to see here. Other than that, they have obviously now a very, very much cash in the bank, $16.1 billion. That's about 4 gigafactories that they can create. Giga supercharger station went up 50%, which is also fantastic. They now can together build more from the capacity, more than 1 million cars worldwide. And we are not talking yet about Berlin as well as Texas. Berlin is almost ready. Texas also is very, very far in advance. Our Fremont produced China factory build-out remains on track with testing of equipment well underway. We expect to receive the final permit approval before the end of this year. So that's also interesting. You can see the market share also by region, also very impressive. US and Canada, number one electric vehicle, obviously. And then you can see here a lot of people now, the autopilot is such a big part of the Tesla revenues in the future. So you can see here that it's quite interesting to see that. Okay. Yeah. Other than that, you can see that insurance is one of a very, very important part here, which will grow over time. And other than that, I think, you can go through it by itself, but I think that, it speaks by itself. Great company, great environment. I would love to work for them, to be honest. And I think that this is just the beginning of a fantastic year. Stock, obviously, because of the expectations, is not now crazy overblowing, and that's a little bit of profit taking here that you have. So quite interesting. Other than that, I want to also go into Bitcoin. Bitcoin went up quite a bit today, as you can see, to 66,000. I think in the highest point it was even 67 almost. So new all-time high, market cap of 1.243 trillion. It's unbelievable, guys. I congratulate to all of you who are in Bitcoin, and don't forget to also follow me on Instagram. Thank you very much for tuning in, and have a fantastic day. Now the next couple of days are also earnings days, and I cannot wait to share them with you. This was a little bit of a long live stream. I will definitely, shorten those and just come on, but I didn't have the chance because I was outside, so forgive me for that. And thank you very much for watching. Take care.